the hell? No, I'm not even streaming. Okay, that was weird. To anybody listening, I wasn't sure what just happened. I think my stream had a little issue, but I think it's back. We're going to give it a chance to be back. Well, hello, that was a rather ignominious start to a stream. Welcome to the July 30/31 edition of the SkyTour LiveStream. And tonight we're going to be looking from the John Zach Memorial Observatory here in picturesque northwestern Connecticut at a bunch of things. And you can see on the screen now we got a couple things going on, but I'll tell you about those shortly. From galaxies and nebulae to double stars, planetary nebulae, and globular clusters, we're going to see it all. And we might investigate something to do with spectra, as you can see. As you know, we'll take questions from chat. If you want to see objects, let us know. It's all live, it's all uncut. So we'll see you soon as the telescope is acclimated. And here we go. Hello and welcome to the SkyTour LiveStream for this evening, the 30th and 31st of July. We're testing a new instrument in the observatory tonight, but we're not going to stick with this the whole night. This is more of a technical thing. It's called a spectrometer, and we're trying to identify the spectra of the stars. This star is Vega, and you know Vega is very bright, but what we're doing here is we're showing it a little dimmer. Now, if I wanted to show it as bright as it can be, well, then I would get down to here and you'd see Vega very bright, along with its spectrum very bright. But we're going to do a couple of little tests as we move here. We're going to try to make this work. And as you can see, I make it move across the screen. That's important. And that was kind of too fast. So I'm going to move it slower than that. It's actually moving. I don't know if you can tell. And we're going to take a photo right now for 1.6 seconds while it's moving, and you'll see why. So the photo's taken, and there it is. And when we go back and look at this photo, we see Vega on the bottom. And the interesting thing about Vega in this photo is that it's sort of dragged out in the little dash. And that's important because we want more data and we want more of a spectrum. What is a spectrum? The spectrum is when we take a star's light, the sun or any other light, or even the light from a lamp, and we break it up into its component colors. This spectral system, once it's running, will be able to actually see dark lines in the spectrum that tell us what elements are present in the atmosphere of Vega. That is the stellar atmosphere, very, very hot. So we're going to do that. We're going to do a couple tests. That's what this is tonight, just a little bit of test. Then we're going to start looking at some things. That the moon is still out. We'll check out the moon for a while. We'll look at Saturn. And I know you're going to ask, hey, can we look at the spectrum of the moon? Well, sure, but it's such a big object, that the spectrum doesn't really tell us too much. Stars are point objects, and spectra are better on point objects. But who can tell me in the chat, and Amanda's out there, who can tell me in the chat what we might see if we look at the moon's spectrum, or say the spectrum of, say, Jupiter? What will we see? Believe it or not, you already know the answer. So that's a question for you. So let me know as the course of the stream continues. Amanda, you're here, correct?
I am here.
There she is.
I'll take a guess after chat has go, because
okay, that's perfectly fine.
my answer is very, very basic, and I'm sure
Nonsense. It's not very basic. It's just that you're curious, and that's what makes all this work. You know, is when people are curious. If people weren't curious, then they wouldn't care.
Exactly.
And you're all very curious people. Very, very curious. Just like me. I'm very curious. So let's go up now.
Okay, so what would we see if we took a spectra of Jupiter?
A spectrum of Jupiter. What would we see? And that's a question for the folks in the chat.
Type that in right now.
And right now I'm going to do another photo of this spectrum that I'm getting. This is not all separate spectrums. This is the same one. But the bright one at the top is called the first order spectrum. And on this side, you see the first order, then the second order. This is actually a system that uses a very finely lined glass grating, it's called. So I'm going to do a 2-second exposure at this setting.
Okay, I got the question in chat and they're thinking about it.
Okay, and now let's go see if this... Now when you look at a spectrum, you don't care about the lines that run through the colors. That is, from the red to the orange to the yellow to the green to the blue and the indigo and violet. Those are actually artifacts created by the grating, which is breaking the light up. We care about the colors moving across the not so wide part of the spectrum, the part that goes from, you know, the left side of the green to the right side of the green, and to the left side of the blue to the right side of the blue. And because we're testing this device right now, there are a few quirks that need to be worked out. And if I were to put the camera on the top of the telescope and use a lens, and I have a system if I mount, you know, the system on the camera with that, then we see a far better spectrum than we're actually getting here with the big telescope. This just means that I have still to figure this out and to work out some of the actual engineering quirks. But other than that, it's not bad, and it's going to be a nice addition to the system, because remember I told you about the color of the stars tells us a lot about the star. It tells us about its temperature, and it tells us, you know, some other things about the star, about what spectral class it might be. You know, from O, B, A, F, G, K, or M. But when we actually look at the star, and we look at the spectrum of a star, we can tell what elements are in its atmosphere, like I said, and that gives us further clues as to what type of star it is. Okay, so because you can get, for instance, you can get a G-type star that's like the sun, and that G-type star can be a giant. In other words, it can be a giant class star, a giant spectral type. And those are types, you know, 1, 2, or 3, as in I, and I, you know, Roman numerals. And if we have stars that are in those classes, how would we know the difference between a star that might be like the sun, you know, about 1 million miles across, and a star that's a supergiant star, that's a G-type star, that's as big as the orbit of the Earth? We have to figure that out. How do you do it? With the spectra. If we look at the spectrum of the star, we can see the elements in the star's atmosphere. If we see elements that indicate that the atmosphere is cool, not very hot, then we know that it has to be a giant. And that's that's a very minimal approach. There's so much more to it than that. But letting you know right now, this is something that would be very useful for us. So I'll give you an idea. Say we look at Albireo, that double star in Cygnus. And I know that right now, we don't have it. This isn't calibrated in any way, shape, or form yet. So I'll go to Albireo and we'll actually look at it with this system, before even have it all calibrated. And let's just see what we get. Okay.
Yeah, we do have a few answers coming in, but
Good,
we also
good.
have some other people coming in, so I just repeated the question for them, so hold
Okay.
off on the answer
Sure.
for now, please.
I can answer it yet.
And the question was, what would we see if we looked at the spectrum of Jupiter?
Right. Now, if you look at the screen now, okay, what you're going to see is you're going to actually see, and this is why this is going to be so much fun for us. You actually see Albireo on the screen. You see the lower star, and you see the upper star. Now, remember the lower one? Remember what I told you about the two stars, right? What types they were? Does anybody remember? I'll tell you anyway. Okay, that right hand, the lower star in the Albireo pair is a K3 giant. Okay, and the left-hand star, if you recall, is actually a B8. So beta 8, B8 type star. So if we were to zoom in on this, all right, we can see that there's something about the spectra which is a little different. And actually, even though it's not calibrated, this is helpful to us. This tells us a lot, even now, uncalibrated. And I'll tell you exactly why. And this is cool. This is real science, folks. So this is kind of cool. All right. So the stars are down here. All right. And we're actually looking at the spectrum of the K star on the right, and the B8 star, K3 on the right, and the B8 star on the left. Do you notice something? Now, obviously the image is bloated, and so it makes the spectrum on the right look, wider, and that's just because of the bloat of the star image. But notice something else. I want you to notice the relative amount of color that we see. The B8 star doesn't, has more in the blue. All right, look at the blue on the B8 star. It goes all the way up, and if you were to take the two stars and put the spectra next to each other, then that blue would go all the way into the green of the star, of the K3 star. And then at the red end, it just sort of tapers off very quickly, doesn't it? And on the K3 star, the red continues for some time. You're seeing the information that we can see even with an uncalibrated instrument. We're seeing the information that's giving us clues already about the nature of the stars. And we see now a literally evidence right in front of our faces that the spectrum of the star will tell us a lot about the type of star that it is. So the orange is going to have light that's predominantly in the orange, and this is exactly what we see here. The brightest part of the K3 spectrum is where? Right in the orange. You see that? And the brightest part of the B3 star is in the blue. Now, it's a little less obvious, but you can actually see that the blue is very, very bright with just a tendency, it's a little bit of the green as well. So you're seeing how the dominance in one color of the spectrum is borne out with this spectral view of these two stars. It's a little different than defocusing the star image to just see the color, but we see the predominant colors coming, and we see the predominant elements that we can see in the spectrum that we currently cannot see because I don't have this calibrated properly. I am gonna, as I speak, and I apologize for the noise. We got this stupid construction stuff going on again. I do want to try and focus this just in case there's an issue. That's the wrong way, obviously.
Okay, Daryl wants to know if you can pick up emission or absorption lines.
Yes, Daryl, we can do both. In fact, what is an emission and absorption line? An emission line is, well, let's go with absorption first. In a star's atmosphere, the core of the star is the hottest part, okay, 15 million degrees plus. And when we look at how hot the star's core is, if we then go out to the outer areas of the star, the outer surface, so to speak, that's much cooler gas out there. Okay, so what it does is it absorbs some of the energy coming from the interior, and that absorption causes a dark band to appear in the spectrum. And I'm looking in here, and we're looking at the spectra live, and it's kind of hard. I can take a very short exposure and maybe see something here. So again, we wouldn't see, we would see these dark lines because the atoms that are in the outer part of the star's atmosphere would actually absorb energy coming through them from the interior. And by doing that, they create a little dark line. And hydrogen gas has specific locations that it pulls out of the overall light energy from the star. In fact, they're famous locations. They're known as the Balmer series, as in B-A-L-M-E-R. The Lyman series, you have the Lyman, L-Y-M-A-N, and so on. So you have different series of absorption lines you get depending on how hot the core is and the type of star it is. So when we look here at a spectrum, let's take the K3 star. Now, if the K3 star was in the last throes of its life, and it was actually had a cloud around it, around the outside that it had expelled, and it was exciting that cloud with some ultraviolet radiation, then that ultraviolet radiation would be absorbed by the atoms in the outer atmosphere of that star because it was very hot, say, and then as soon as those atoms in that outer area spontaneously emitted their photons, just like the hydrogen series, these atoms would emit in a specific location, in a specific place in the spectrum. And you'd be able to identify exactly. And when they do, the lines aren't dark bands, they're actually bright lines. And they also go by the name of bright line spectrum. And a bright line spectrum is something that is, again, a very interesting, it's a very interesting and very deep subject, actually. And I think eventually we're gonna do that, because when we go to planetary nebulae give off emission lines, and it would be really cool to see if we can get the emission lines. Once this is calibrated, we're gonna go there, and it's gonna be really cool. Now, I'm gonna try, just as a last ditch here, I'm gonna try to see if I can get a line here, some kind of a absorption lines, because the star, the B8, should be able to show us some lines. Now this isn't going to probably work, and these spectrums are going to overlap, but we're going to try it anyway. Okay, let's see what we got. Oops, hold on. Well, I just need to calibrate this some more. But
and again, we weren't sure that this was going to work.
No, so yeah, you're right. I've been saying it's not even calibrated to the telescope yet. Yeah. So I have more work to do. But I am actually I'm seeing that if I were to put this through my spectral system, that the K3 would definitely give me what I need. So we're actually seeing these lines, although they're a little bit soft. That is, soft-edged. But stare at this for a minute. I'm just going to let you stare at it for a minute, because I want you to see that. It's something that we can actually explore further as we start to get into spectra at some point. But you're looking at the major tool that we use in astronomy in order to see what's going on out there. We use the spectra of these distant objects to tell us what's going on. Give you an example. If a star is out there in space, you know that it's moving around the galaxy because we've talked about it. It orbits the galaxy every 230 million years. It orbits the galaxy, and from our location actually, that 2/3 of the way out. So a star that orbits the galaxy at that rate is moving through space. Well, how do we know that? How do we detect the speed the star is moving? Well, the way we do it, and we can only do it relative to our motion, is if we take a spectrum of the star and we see these lines of these series that I told you about, the absorption lines. Well, these absorption lines might look like they're shifted off of where they're supposed to be. So if you're supposed to see a line at a certain location, and that location is measured in nanometers. It used to be angstroms, and that's just a measurement in a spectrum that tells us where the line is. So we know a specific set of lines in a specific set of places for a specific star and a specific chemical element like hydrogen. So let's say Balmer series. So the Balmer series has a bunch of dark lines that are spaced away from each other, and if those lines all together were being shifted, just say a few nanometers to the red, then we know that the star is going away from us because we're seeing what's called Doppler shift in the spectrum. And the lines that we see in the spectrum end up being moved off of their normal location. So we can actually just look at the spectrum and say, oh, that's supposed to be the Balmer series of hydrogen, and guess what? Those lines are not in the right places. They have moved. Therefore, because the lines have moved, we know that we have a Doppler shift going on, and we know how much that Doppler shift is, and therefore we can actually tell how fast the star is moving, and that gives us a lot of information about the system. So that's how we do it. I know I'm oversimplifying, but at some point, maybe what I'll do on a cloudy night is sort of take you through determining how fast a star moves, and we can go through it, on a live feed where you're looking at my screen, and I'm bringing up things, and I can draw and show you stuff, and you'll actually see it directly. It's a really cool process. Anyway, so this is the spectral thing, and that's Albireo that we're looking at there. And as I said before, the K3 giant is on the right, and Albireo, the B8, is on the left. Look at the length of the red part of the spectrum for the K3, and look at the length of the red part for Albireo. I'm sorry, for the B8. Okay, most of the energy coming from the star is focused in the blue for the B8 star, and focused in the orange for the K3. And it's borne out by the spectra. You can actually tell which star is probably hotter just by looking at this spectrum.
Yeah, I was thinking about... I'm thinking of all these basic things I didn't understand in science class, and our good friend Daryl is in chat, and he was saying that the more blue means the hotter it is.
Yeah.
And the more red means the cooler it is.
Very good, Daryl. That's right.
But yet when you think when you think cold, you think blue, and when you think hot, you think red. So it's very odd.
Yes,
why?
It's a strange dichotomy we play with there. But yes, the hottest.
But then
stars,
extremely hot fire looks blue, right?
That's right. The hottest part of the flame is what color?
Blue. Yeah. So
right.
That makes sense. But the red to be cold, I'm not getting the connection there.
Well, it's only because you know that the blue part of the flame is the hottest, and in that same flame that it tapers off, and you actually see that the flame goes to like an orange, and that's not as hot, and that's the whole point.
Very clever.
That's the whole point.
See, and even like basic art, the three primary colors were red, yellow, and blue, but yet in science it was always red, green, and blue, which I never understood. I'm like, how can green be, without the yellow? Where does the green come from? But we're looking at it. Those are the three colors I see. When we look closer, I can see the oranges and yellows and purples, but
keep in mind what's
It's
going
different
on.
with light,
It
right?
you just said what I was going to tell you, so you figured it out. Light is different. Light is not paint.
Mm-hmm.
You know, when you add all the colors of light together, what color do you get?
White.
You get white. When you add all the colors together in paint, what do you get? Brown, goo, right?
Yeah, like a
Right?
grayish.
Right, you get
Gross,
this
yeah.
disgusting mishmash. So yes, and that's exactly right, and that's why we cannot think about art class and try to understand light. And that's why science is you know, science has its own agenda. You have to allow science to tell you. You have to allow science to share with you and make you aware of these very important facts, because this is actually how it all works. And you know, we get it. We get it. You know, we actually can, you know, we can actually figure it out. You know, we're pretty good at this stuff. You know, those of us who and all of you. I mean, those of you who listened in science class may not understand it, but when you listen in science class, you've learned more than you did when you didn't take science, and that's something that is very very good to know. You've learned about light tonight. We learned about the different colors of light and how the star spectra can show us exactly where a star's main energy is coming out. And that's exactly what this is.
And that's why this is such a brilliant channel, because, I mean, you can understand these in a classroom. Like, I mean, I knew, even though I didn't understand it, I knew light was different than paint, and for some reason it's green instead of yellow. But now you are showing me. Like, it's kind of like, okay, now I get it. Because, you know,
well, yeah,
you can memorize facts and you can think you understand it, but until you see it, then it's, you know, I don't know.
No, you're absolutely right. This is live
incredible.
science.
Yeah.
This is live science happening. So I think that's pretty cool.
It's very cool.
And I'm glad that that there's people that are not sleeping out there and want to watch this stuff. You know, I'm very happy about that. You know, you guys are wonderful.
Oh, everyone is really excited to see what you're bringing us tonight. Yeah, a few people knew straight away. Ooh, we're doing spectrums tonight, and
cool.
You know, I do have a few guesses. I don't know if you wanted to hear them before we forget about them, or.
Oh, I'm not forgetting, because it's very important to understand this. So go right ahead.
Okay. Well. Okay. The question again was, what would we see if we took the spectrum of Jupiter?
Correct.
Okay. So, Merck said we'd see diffracted light relevant to its chemical composition.
We would see the light spread relative to its elemental composition. That's correct. I mean, that's one thing that's correct. Keep going.
Okay. Now Maddie stole my answer. We'd see the colors of the rainbow.
That's also correct, because the spectrum is by default that. So these are all correct. Yeah. But there's one thing I'm aiming for.
Now Daryl said,
Daryl's gonna know.
If you could,
Daryl's gonna know. He'll know. Come on, Daryl.
Well, hold on. Okay.
Do it, man.
He came in a little late. I had to repeat the question for him, and I may have misled him. But he said, if you could, hydrogen mostly, I would suppose. Merck said in the past, what we see is ammonia, I think, at Jupiter's cloud tops.
He's right, but
still not the answer you're looking for?
Not exactly, no. And I'll tell you why.
Okay, give him another 30 seconds.
Okay.
Can you guys be more specific?
Yeah, you can be more specific, guys, but that's all right. All right, I'm going to Altair right now.
No one's wrong. No one's wrong. That's good.
No, it's not wrong. It's not wrong. All right, I'm heading over to Altair now from Alberio. We're going to take a look at Altair, which is an A7 star. It would help if I get the dome out of the way. Yeah, look at that. Isn't it great? There's Altair. Okay, so let me bring Altair in closer. I should not closer, but I'm going to move it up for us so we can see it. Okay. And then, alright, now I'm going to move it over here. We'll go actually over there. Alright, and what I'm going to do is I'm going to do the same thing I did before. I'm going to take a photo of the spectrum. And see, the reason I take a photo is because if we look at this spectrum, it's not helping us. It's too thin and it doesn't have enough breadth to it. So I'm going to actually cut down the amount of light that we're seeing tremendously. And then I'm going to move us in by taking a photo. Yeah, it's a little too fast. I'm going to slow it down. Try this. Let's see what we get. This might be too bright, but we'll try it. This is going to be a 2-second photo of Altair in the spectrum. Okay, let's see if that's too bright. I can tell. No worries. We'll just dim it down. Yeah, too bright. And remember, the colors that run the whole length of the spectrum are not the ones we want. I'm sorry, the dark lines that are running the whole length are not what we want. We want the ones that are running within the color. So from one side of the color to the other side of the color. Those are the absorption lines that we're looking for. Okay, now let's see. Let's go to here and do this again. I think I still have too bright. It's trial and error, you know, folks. It's just sort of trial and error. Yeah.
Yeah, but you never know what you're going to catch in trial and error.
No, you're right. But I'm going to actually, that's F25 at 160. I just have to go a little faster, that's all. Try this. That'll be pretty fast. But let's try it. Why not? Sorry about the noise. There we go. See, now we got it spread. And if we look at the result, it's almost like you got to turn your head sideways and look like top to bottom. Now Altair is an A7, so the light from Altair is actually almost white, actually. And we know white light is evenly made up of blue, green, and red. And what do we see there? Even makeup of blue, green, and red, don't we? And when I get this calibrated, we'll actually be able to see the hydrogen series lines. You can actually see some of them. They're kind of fuzzy there. But you see in the border between the green and the blue, you can actually see a line that's running kind of upper left to lower right there. That's one of those lines, a very broad line. And there's another one between the green and the red over there. So we're gonna get this straightened out. Because once I do, I really think you guys are going to be really interested in what the spectra can tell us. Because it's really something.
We do have a few more guesses.
I'm waiting. Go ahead.
Okay, well, Mark wanted to elaborate on his. He said temperature, direction, chemical composition, age, something like that. Any of those?
He's getting a little colder now.
Colder? Okay, now Maddie came up with something very, very clever, I think. Okay. Would we see the same spectrum as we would from the sun, as it's basically reflecting the sun's light back to us? Planets don't emit their own light. They are just reflecting the sun's light.
Oh, Maddie, you gotta tell me if you looked that up, or if you just know that you synthesized that, because that is the exact correct answer.
Oh, right on! Yay, Maddie! We were all hoping for him.
No, nice.
That is brilliant.
Very nice, very nice. Yeah, that's exactly right.
Oh, that's so good. Congratulations, Maddie. So good.
Yeah, that's cool. See, it's like a little game. We can do all kinds of astronomy games like this. I can tell you that.
Oh, I love games.
I know you love games. I know that because I heard you with Bill. You've done some really cool games yourself, actually. With was it Family Feud you guys played?
We play Family Feud a lot, yeah.
Yeah. All right. Now I'm going to go to another star that I want to show you with this system before I take it off, just to kind of. We went to like an A star, and we saw a B star with Albireo. We saw the K. Now I'd like to take us to another star that is more more toward the red end, it's going to be an M class star. Okay, and you know the star, but you'll recognize it. In fact, from its spectrum, you could probably tell what it was once you know about spectra. But let's just check this out.
And Maddie swears he did not cheat.
Well, well done, Maddie. That's fantastic. Fantastic. You're absolutely right. See, because the light is reflected from the sun, off of Jupiter, we do see only the reflected light of the sun. Now, we can also tell because the reflected light is still energetic when it gets to Jupiter, and that reflected light will indeed reflect. It'll reflect off the planet, but as it does, then the chemicals within Jupiter's atmosphere will actually cause some additional absorption lines. So here's what we do. Here's how we figured out what Jupiter's made of without using the space probe. We actually took a spectrum of Jupiter, and when we looked at the spectrum, we compared it to the sun's spectrum. The sun spectrum has a special name, and I'm sure some of you in chat know what that special name is. It's called the Fraunhofer spectrum. And if you look at the I was looking at something weird on my screen from OBS popped up. If you look at the spectrum of the sun and you compare the spectrum of Jupiter and you subtract the two from each other, only those things present in Jupiter, okay, will be left. So that's an interesting technique for finding what is in Jupiter's atmosphere. And doing that, we found that there's ammonia. Okay, we found that there's hydrogen and helium. And it's really cool the way this works. Now, this, what we're looking at right here, you'll notice that it's jumping around a lot. And the reason it's jumping around a lot is because it's kind of low. It's not very high up in the atmosphere, high in elevation, altitude. And you'll notice something else missing. It doesn't appear to have much green. I'm sorry, it doesn't appear to have much blue, does it? The dominant colors of the spectrum are more toward the red entirely, with a little bit of the green, huh? Okay. This is Antares. This is the M1 supergiant, Antares. And we're going to take a spectrum of Antares too. I'll just do a spread out spectrum so you can actually see it. So I'm taking it now. Here it goes.
There's a lot of really cool information coming in chat here.
Yeah, I think it's fantastic. Let me hear more because I can't see it.
Yeah, no, well, I mean, while you're taking pictures. Yeah, well, no, Maddie was just commenting that he knew that planets reflected sun's lights back to us just as the moon does.
Yep.
And then Daryl said when comet Hale-Bopp came in '97, it showed a huge broad dust trail, and the tail.
Yep.
And it was the color of sunlight, all reflected light from the sun.
That's right.
And the comet showed a narrow gas tail, sort of blue-green color. Spectra revealed what gas it was.
That's correct.
And then John jumped in here. Hi, John.
He said, wait a minute, hold on, before you go further. That they call it the anti-tail, the plasma tail versus the dust tail on a comet. And that plasma tail that you saw that he was just talking about, which revealed what gas it was making the plasma tail, that was an interesting thing because the two spectra would be very different. The dust tail would show absorption spectra for the stuff left behind, and that is to say the stuff in the tail that was made up of whatever it was. You could actually identify it. You could identify probably water in the spectrum and other things. But the plasma tail would be emission lines. They would actually be the exact opposite type of spectrum because that's actually excited atoms emitting rather than absorbing, cool atoms absorbing. So that's what's cool.
That is very cool. Yep.
It's
so hard to get your mind around some of these concepts.
It takes time.
I mean,
I'm giving you the shotgun approach every night when you do this. Take a look at the screen. All right, Antares is the red star around the bottom, along the bottom. And if you notice, and once it's calibrated, we're going to be able to see those lines that are running along the colors a lot better. But if you notice, they're kind of fat and broad right now. They actually they could be a lot thinner and smaller and more workable. But right now we can't see that. But we'll get there. I just have to do some more calibrations, and I'll take care of that. Tomorrow I'll actually call the guy that worked with me initially with the spectral system, and I'm gonna find out, because it's the weekend, so on Monday I'll talk to Tom and I'll find out if what I can do for getting the spectral readings this way. And if I have to buy a different spectral system, I will. But look at this. This is telling us a lot of information just by looking at this. Notice if you squint at the screen, you see that green and red are the dominant colors and blue is almost non-existent. In all the other stars we looked at tonight, we saw plenty of blue, didn't we? Alright, and here we don't. In the A-type stars, the light is white, so we'll see an equal measure of blue, green, and red. In the M stars, like this one, we see only red and only green, with the dominance being in the red. Excuse me. So this is where I'm going with this stuff. I'm trying to start you down the path of understanding how stars actually work, how they actually do what they do. And when we look at the spectra of the stars, that starts us down the path of science and learning about what's really going on, and that's just cool. Now, once the system gets better, then we'll be able to take and look at emission spectra as well, and we'll be doing that as not too distant future, meaning like a week or two, maybe 4 if I can't get the parts. Anyway, so let's go to another star. Actually, not a star. I kind of gave it away, but we're going to go look at Saturn. I would like you to see Saturn. And you're going to say, well, I want to see the sun spectrum. And the answer is we're not going to be able to yet until I calibrate the system to show it right. But I do want to show you what we're looking at. Okay, so...
Yeah, well, that's what they were saying in chat. Astronomy LiveStream is in here saying the light bounces off elements which the planet is made of. So from the spectrum, we know what elements the planet has.
Right.
And then John jumped in and said, the moons of Jupiter are the reason we know the light of speed. Is that true?
Wait.
How did that happen? I'd like to hear that story.
Wait, what was that?
If you know it.
I couldn't...
John said, the moons of Jupiter are the reason we know the speed of light. Is that true? I'm asking if that's true. That was his comment. And that sounds really interesting if you knew that story.
Yeah, I actually, there were a number of experiments to confirm the speed of light. In fact, one of the more important ones was that during an eclipse, when they saw that the starlight was bent around the sun, literally, starlight was bent. The positions of the stars were a little bit different. They realized that the starlight was being bent because it actually has a mass. Light has mass, which was a huge finding. It's Einstein's, it was an Einstein postulate and ended up becoming science fact. This is Saturn. Now, why does it look this way? Can anybody tell me? I want to know if anybody knows why we're seeing it like this. It looks like it's like a little spectrum on the left, there's one on the center, and then one on the right. Well, what is that? Why do we see it this way? And folks they will see the question from you before they hear it from me.
If I can type that fast, hopefully.
That's okay. By the time you finish typing, they're going to see it.
I already have an answer.
You have an answer, or?
No, an answer from chat.
Oh, you already do? Mm-hmm. All right. Tell me what it is.
Is it the rings? The gaps between the rings and the planet body?
Exactly. We're actually seeing the rings. Because the rings are also reflecting sunlight. So we're seeing little tiny Fraunhofer spectrums on the left and on the right. Now, by looking at the spectra of the rings, we can determine what they're made of once we have the resolution to see that. And I don't know if I'll be able to get the resolution with this telescope. We might have to use a refractor, which I actually have. Yeah, I should have told you, but I didn't. I actually have a second telescope that can go on this big beast and ride along with it, and we can actually do spectra through that in the same way that we do here. So we can actually have multiple sources that we could see on the screen of multiple instruments. Right now we're only seeing one camera. We're not seeing two, except for the one that's in the observatory that you see in the lower left-hand corner with me. But that's about it. Once we get the other instrument in here, then we'll have another camera to put on there that will have the spectral system on it, and we'll be able to see that. And it's going to be just outstanding. So, now that I gave it all away, let's go back here. So now, so this what I wanted to do was actually show you just a little bit about spectra first tonight, before we went off and did other stuff. And for those of you who want to see the moon, I'll show it to you with the spectral system, but you'll be really somewhat disappointed because you'll say, what's that? You know, what's going on there? But here's Saturn, just so you know. Okay. All right. And then once we see Saturn, we can go up and see how its spectrum looks. You see that? Its first order spectrum shows us the rings. And so that was a very good answer. And well done to you guys. I'm so proud of you. Jeez, you know, you guys are so smart. But anyway,
and John filled me in on the rest of the story.
Awesome. And now the rest of the story. Well done. Great.
That's why I cannot say enough wonderful things about the people in chat. I mean,
aren't they something?
It's like they can anticipate the things I'm gonna ask, or they can tell when I've lost where we are in the conversation, and just a little extra tidbits, and
they help
you know,
you
or they'll spell words properly for me to look up later, or send me a link, or guys, chat, you're so wonderful. Thank you so much for the continued support.
Yeah, absolutely. Thanks, guys. You're doing great. Thank you so much. All right, I want to take you now to another place. We're going to go right now. Moving. Whoops. Okay. Yeah, there you go. So now, this is your ever-loving moon with this spectral system. Now, you might say, ew, that's gross. Why would I even want to, why do we look at this? That's disgusting. You're right, it is, all right? And here's why we're doing it. We're doing it because we're just showing how, I'm doing this actually to show you that there's no reason in the world that we would use a system like this, the very same one I'm using, like this. And when we do spectra of large objects like this, we do something called a slit spectrogram. We actually admit only a tiny little bit of light into our spectrometer, and that tiny sliver of light will display the entire spectrum to us. All right. If we just look at the big giant object, this is what we see. But if we were to have a little tiny slit, then the brightest part of that moonlight would be reflected in, and it has all the information in it. We won't lose anything by just cutting out a little tiny piece. And so this is something that is very important, because doing a slit spectrogram is something that we're not doing at the moment, not going to do at the moment. So this spectral system I'm using is only for stars. Won't work on the moon, and will work very poorly on planets. And to just prove that, I'm going to go, or will I? Uh-oh. Yeah, I don't think Jupiter is available anymore. Well, we saw Saturn. So
you said something about the sun's, I don't know, the sun's particles still being active by the time it reached Jupiter?
Well, yeah, the sunlight is energetic, you know, and it will still have energy, solar wind, and the particles will still energize atoms in the atmosphere of Jupiter. And it's the intensity of the light that will. Now, it's much less, okay, but people, believe it or not, people have actually taken the spectra of the planet Uranus and Neptune themselves.
That's what I was gonna say. You said it will go as far as Jupiter, like maybe it will only go so much further past it.
No,
So they got to Uranus, not Pluto.
Yeah, no, it will, but see, and Uranus has an atmosphere, a heavy, thick atmosphere, and by doing a spectral analysis of the light coming back from Uranus, what's removed from the spectrum is the absorption that was due to the atmosphere of Uranus itself, and similarly for Neptune. And so there are papers out there, people have done it. I don't have a spectral system that can do it at the moment, but I will, and we're going to be able to see the spectra of these very, very larger objects. We have to do a slit spectrograph. We have to get a slit spectrograph, and a cheap one is around $600, and then it takes probably a month or so to calibrate and get running. And I don't want to do that over the winter. I think that's something I want to do when I'm in Arizona with all this. So that would be a much nicer place to do this. So I'm not freezing my fingers off trying to tighten a little thumb screw and do a calibration. But here's the moon. It's disgusting looking, and but that's what you get because it's a big distended object. And by distended I mean big bloated out large object. And when we use a slit spectrograph, we will only see a tiny slice, and that'll give us the spectrum we want. So, speaking of tiny slice, let's actually go to one other place, another star that is very close to this. And we'll have to make an adjustment to be able to see it. Okay, let me just bring it in so you can see it. There it is. Little guy out there. This is called Zubinel Acribi. It's Delta Librae in the constellation of Libra, and it's right above the moon. I'm a Libra, by the way. And
I knew it.
What? How did you know? How did you know it? How did you know it?
Well, should I give away my super stalker secrets?
Oh, you just saw my birthday and figured it out.
No, I looked for your birthday actually because I don't know. I don't know why. I don't really know about other people's signs, just mine, but a lot of my best friend is a Libra.
Oh,
and
cool.
Just people I've gotten along with really well happen to be Libras. I like the whole balance thing, and
okay.
And I wasn't surprised to hear it. I heard you say it yourself, actually.
Okay.
You slipped up, and I caught it.
I wasn't hiding it. Yes, I was born on October 17th. And I believe that it's actually it's good to be Libra, and guess what? It makes no bit of difference whatsoever.
Well, they have the whole thing now where we all would have been shifted over a sign anyway, right?
Yeah.
So what would you have been, a Virgo?
I have no idea. I don't know. Oh, I mean, maybe a Virgo, because it's Spica's right nearby. We'll see. I don't know. All right, let me.
I was always meant to be a Gemini, so.
Oh, okay. Well, Gemini's a great space program. Okay, so.
Why do they pronounce it Jiminy?
Because they didn't know any better, actually.
Really?
It's actually Gemini. Yeah. Not Gemini.
Yeah. I always hear that, and it really, really bugged me.
Yeah, it still bugs me. When you said it, I twitched. I mean, that's like,
Oh, you probably heard the displeasure in my voice when I had to mispronounce it.
Yeah, really. It was like, come on, man. This is, as I said, this is Zubinel Acribi. It's Delta Librae, and you'll notice that this particular star has a healthy blue, healthy green, healthy red, but it has a dominance of green, and the interesting reason for that is because this particular star is actually like the Sun. This is a G8 star. However, it's a subgiant. Remember I told you about we can't, and this is why I'm showing it to you, we can't decide or we can't determine when we look at stars If they're G stars, we can't determine what type of G star they are. They could be a giant, a supergiant, a subgiant, a dwarf like our sun, main sequence star like our sun, you know. And we wouldn't know unless we could see the spectrum, and then we could tell by looking at the spectrum, perhaps, if there's certain things going on that would indicate whether it's a giant of a particular type or a dwarf of a particular type. Really cool stuff. And so what I'm going to do now is I am going to just take a quick, let's see, what am I looking at here? Okay, not 5 seconds. I don't want to do 5 seconds. I want to just do a, sorry about that. I'm going to do a 2 seconds on this. It'll be kind of small, so maybe I'll do 2.5, 3.2. Here we go. We'll try this. Let's see how fast it's going to move. Well, that's a little fast. Let me just slow the speed down a little bit. And here we go. Okay, now we'll try a little 2-second exposure while we're moving it. And it might have been not good enough. I might have to do a little more, and go up in ASA a little bit. There, let's try that. Yeah, see, not quite right, but let's take a look at it anyway. Again, like I said, not calibrated, not correct yet. We don't know what it's doing yet. But this star is more like the sun in terms of you know, the spectral class, but it's not like the sun in terms of the total spectral type, because its luminosity class, its brightness class, it's a subgiant, so it's a 2, II, you know, the Roman numeral 2, meaning it's since stopped making hydrogen into helium in the fusing process, and has left the main sequence. That is where it lived for much of its, you know, for a lot of its life, like we are here now in the main sequence, and we're happily fusing hydrogen into helium overall. And this star has left that behind, and we could tell where it is by examining its spectrum. And when I get, like I said, the better resolutions, we'll be able to see that. So it's kind of cool. I'm really loving this. I'm glad we took this little trip tonight on this. Now, as far as, oh, you know what? Okay, we're gonna do one more thing. It's like I'm fighting with myself. I'm ready to take this off and put on the regular camera lens, and or, sorry, take it off entirely and just put it in to look at obviously things in the sky. But then I'm thinking, oh wait, there's some cool things we can do. We can look at some neat clusters. That would be cool. So before we do that, I want to look at one more variable star. I'm not sorry, variable double star that you know very well, because we've seen it a few times, and it's literally almost overhead. So we'll do that with the spectral system here and see what we got. All right, let's go there now.
Double star, we all know well, right overhead. What is it?
Very good.
And my fingers don't want to work properly tonight, so please excuse the typos in chat, guys. They're also apologizing for not being able to spell or misspelling the two bright stars in Libra.
Oh, okay. Yeah, well,
I couldn't even spell Pisces right. Like, don't worry about it.
Zubin al-Akivi is not like the easiest thing in the world to spell, so I can't hold it.
He spelled both of them. What's
right.
the other one called?
What's that?
What was the other one called?
No, Zubin al-Akivi is the name of the star we just looked at.
Yeah, there's two. They sound similar.
Oh, Zubin Ganubi is another one that it has Zubin in it. Yes, as you see Zubin and you think it's the same, but it's not.
They're not the two bright stars in Libra?
Maybe. I'm just sorry. I'm looking at trying to do something here. Oh.
Is it Alberia?
No, Alberio's in Cygnus.
Oh, that's not where we're gonna go look at now, I mean.
No, actually.
Oh. Ooh.
This is, oh, sorry. This is speed. There. Okay, let's try this. This is going to be fast. I just want to move it over. Get it near the center, and then we can go look. Okay. So now we drop the speed down to this. And how are we doing? Sorry, I'm just getting my speed set here, sorry. That's what I want. Sort of. Okay. This is actually an interesting set of stars. This is in Lyra, and it's Epsilon Lyra. It's a double-double. Okay? And this is one pair of the double-doubles. Actually, I'm not sure if this is the this might be the two together, actually. Yeah. So each of those is a double star, and the the spectrum that we're seeing is the sum of the two stars. We're not seeing them separately because we don't have the magnification or resolution with a wide field telescope like I have here. This is a wide field scope that we're using, and so when we do this, we don't actually see the four stars that are in this field of view right now. And that's what there's four stars here. Okay, each of those look like one each, but there's two and two, and they're so close together that we don't actually see them as a separate spectrum. Not with this resolution anyway. But I could do magnification and probably show that, but anyway, I'm gonna do a quick photo just because. Let me try this. Let me get out of this. And it has to be short because, you know, moving that much is going to cause the spectra to overlap, so I have to be careful. Let me go to this speed and see if this one will do it. That will. Okay, so we're going to go to a very high F ratio, like that. And we're going to do 3.2 seconds. We'll try that. And here we go. There we go. Taking the picture. Oh, good. It worked. I didn't know if it was going to work, sorry. So, there they are. You see the stars. And you can actually see their spectra. And we're going to be able to figure out, like I said, I'll get it once it's calibrated. We'll get it all figured out. And we'll get those lines nice and sharp, and they'll be better. And right now they're not, so I apologize for that. But I just want you to be able to see how you can get two stars that are nearly identical, can have, you know, two nearly identical spectra. And again, when we looked at the spectrum of Epsilon Lyra, we actually saw that these stars were indeed, you know, very, very close. And again, it's a summed spectrum. It's a spectrum of four stars we're looking at right now. So because the light is conflated with the light of each star, of the two stars, the light does get conflated, and that's a problem. But it's just kind of cool looking at the spectra and seeing how much information is in there for us. You know, I'm looking at it on the screen, and I can see the faint lines that I want to see. But I'm gonna have to calibrate it to, like I said, to make it better. I apologize for that. I feel like it's almost like a failure. I wanted to get this to work for you. Anyway, what I'm going to do now is I am going to remove the camera and remove this system and put on my regular through the scope system so we can actually see what we're looking at. And I'm trying to. It's here somewhere. Is that it? That ain't it. Oh, I took it off and I put it there. There it is. Sorry, I moved it. Okay, so. Okay, we'll do this. And we're going to do that. Cover it up. That's the thing you do too whenever you have a telescope, you learn quickly that you cover up your system when you don't want other bad things to get into it. And that's just what I'm doing here. So now we're going to go see Epsilon Lyra in regular light with the camera. And that should be pretty interesting. Oh, it's a plane going over, that's what you're hearing. Okay, so let's see what we got. Well, there it is. Now, it's not as exciting because it has to be focused, as you can tell. You can see that. But while we're defocused, let's take a look. They're not orbs. They're not UFOs. It's just Epsilon Lyra. There we go. See, while it's defocused, we can actually see the color. See? And these are obviously very bright stars in their own right. I think we've talked about this before. The stars are pretty much like A-type stars. I say pretty much because the stars vary individually, but they're A-type stars. So the color is pretty much white. Alright? So, let's go back and focus. And now I want to try something. Just try something a little clever because I'm trying to be a little clever. I want to see. Oh, I gotta get off F13. I want to get to, you know. Oh no, wait. Actually, I want to go really high f-stop. All right, and see how that looks. Oh, not good enough. I'm doing critical focusing right now. I just want to try something. That's about as good as it's going to get. So, now I want to go down to just a fraction of a second. Make this almost dim. And we'll try this. Okay.
See, that's what I was wondering with the spectrums. If you took it for half a second, wouldn't you have the best chance of seeing the lines rather than stretching it out and having them be faint or...
No, that's not how the spectrum works. The spectrum works by, literally, you do a drift photo. You'd actually drift the star so that you actually get that line to appear, because the wider the spectrum is, the bigger those lines are. That is, they show up better. So that's why we do that.
No, I know, I understand that, but it's just how can you be 100% sure that it's just not the camera picking up that piece? That you're really seeing the line, not a glitch, you know?
Oh, yeah. Well, you can't. You know, I mean, that's the way you unfortunately have to deal with it. Okay, I'm gonna, this is at ISO 640. I'm gonna go up a little higher. Let's go to normal ISO here. Oh, here we go. Some idiot coming up the street. Yay, I can race. Now, pardon me while I throw a tack strip out into the road.
I'm just waiting for the day we hear a big loud squeal and we see a tire fly by the telescope and...
Oh, no, we won't see that.
No.
Alright, let's try, okay, this is too big. Let's go to 800 ASA and, let's say 4 seconds. Now why? I don't know, I just want to. I'm actually trying to gauge the light to see what we got. Alright, so 800 gives us this. which is kind of what I expected about what we see with our eye. And now let's go up to, say, 2000 and do 4 seconds. And you can see now that things look a little different. We have more stars present, visible. And look at that. I mean, that's kind of interesting, isn't it? That in between them is another pair of stars that look like a double star, but they're not. They're just they're at very different distances. But it's just clever to see these. And now I'm going to go up and do 10 seconds. And you may ask why I'm doing that. And honestly, I just want to see what there is. I just want to see it. It's my curiosity. Isn't that pretty? That's just really pretty. You know? I mean, this is pretty. Okay. This is what it looks like. So we get to see all the stars. Now, those of you that were with us last night, you saw that we had this unbelievable night. Well, we got another night like that tonight. It's just beautiful here. And I just can't, I don't know, I'm at a loss for words because, you know, the moon is still out and I already see the Milky Way anyway. So it's really, really nice. It's just beautiful. So let's see now. Where do I want to take you tonight? There's a couple places I want to take you to here. If anyone has any requests, feel free. I'd be happy to take requests. I'm looking now at this object. Let me see what I'm...
They're saying that I have an echo all of a sudden, like I walked into a tunnel. So I don't know if it's, I'm trying to mute when I type. I know you can still hear it coming through from time to time.
That's okay. Well, what I'm wondering is whether it's a bandwidth issue. If the echo occurs only when there's certain bandwidth that gets taken up or whatever. I don't know.
Well, that's what I'm thinking, because I mean, I haven't touched anything.
Yeah.
You know, other than, I mean, I was going on mute from time to time just so you didn't hear
Sure.
constant typing, but hopefully it's clear now. Can we see Aldebaran?
Aldebaran, no, it's winter. It's a winter it's a winter star. It's the eye of the bull. The eye of Taurus the bull.
Okay,
so no, we can't see it.
Stay tuned. We'll keep that in mind for future.
Oh yeah, well, you'll see it when it comes up. You're right. Yeah, I'm cranking up the ISO sensitivity little by little here in 4K mode, so you can actually see the stars appearing out of nowhere. So you can see, and what's interesting is, as far as you can see, and if you look farther, there's another star, and there's a paradox called Olber's paradox. That's Olbers, which says that if there's stars everywhere you look, then how come we just don't have a very bright sky? Because wouldn't we see the combined light of all the stars, you know, coming at us and reflecting on us, and wouldn't we just see all bright white for sky? It's a very interesting paradox. Until you look at the construction of our galaxy, there's a lot of stuff that gets in the way. You know, and it's kind of cool, but you know. So let me show you something here. I'm gonna come down. I'm gonna increase my speed a little bit here. As I'm going down here and I'm going over, not that way, this way. And I'll just take my speed and go a little faster than this. Speed, and we'll say that. Alright, I have a speed now that's more reasonable. Okay. Now, just look at right in the middle there. Right in the center. There's this little tiny thing right in the middle there. You see a little tiny collection of stars. I mean, we would never see those if we weren't looking at these right now. And you got to wonder, who else is out there right now, maybe even looking at these little stars? The little tiny stars, little 3 stars and 2, very nice, very little stars. Yet we don't have any idea what they are. They're part of the Tycho catalog of stars, or the SAO catalog, or the Hipparchus catalog, or the HD catalog. I mean, we catalog stars. We name them. We give them designations. But then they sit there. They sit there out there forever. We don't even know when they come or go. Must be lonely being a star. But it's really interesting to look at them this way. And I actually like looking at stars. I remember floating through, and I would float through the Milky Way, and I would just look at the stars so often. I would just stare at them, and I wouldn't have any idea, if they were still there. But I always knew that every time I would increase my sensitivity, with like a film emulsion, that would be like a 400 versus 200 film, I would eventually see more stars, and more stars still, and then again, more stars. It's great, because the universe is just so full of stuff. So full of stuff. So anyway, I know that's a little bit of a ramble, and I apologize, but I just wanted to show that to you and go through that with you. Now, one of the other places.
John would like to see the Pillars of Creation. Says that's cool if we could go there. I'm not sure that might look right.
M16. That's the Eagle Nebula. Yeah, let's take a look at what's over there. Where is M16?
Jello asked a question too. He stepped away for a second. I'm not sure who's going to hear this, and I'm not sure what he meant. But Zone 3, up where the timestamp is, he said there's a red light. What causes the pixel noise to turn red sometimes? I'm not sure what he's referring to. If it was something earlier.
Yeah, he's referring. The problem with these cameras that are super sensitive is you get something called amplifier noise. And the amplifier noise will sometimes look red. It'll look like a little red glow. And so if something is going to cause a pixel to spark off and basically produce a little artifact, then it'll most likely be red for this particular camera. So that's what we're seeing. It's not a real thing. It is an artifact of the camera construction and so forth. And yeah, I don't like it, but I can tell you this. Compared to what I had for a camera before, this is really quite amazing, and I'm happy. I'm happy that we have it. Now I'm going to go to the Pillars of Creation here in just a second. I do want to take us to one other place first, and we're going to go there right now. It's not far away. Don't worry. We'll get back. Are we going to be coming back? Don't worry. Don't worry about me. I'll be fine.
So, and you may have mentioned this, and I may have been distracted in chat, and I apologize if you already explained this in length, but I think it's when we were looking at Epsilon Lyra. No, it must have been after that. There were like 2 really bright stars. We could see a whole bunch of little dimmer stars and different, brightness stars all over the place.
Yeah, that was Epsilon Lyra a few seconds ago.
It was, okay. What if you took a spectrum of all of them? Would you not just see like tons and tons of rainbows coming from each star?
Well, yeah, you would, and that's the thing. We want to. I want to find a cluster and just use and do a spectral analysis of a cluster.
Yeah,
so you could just
that's what I was thinking.
But they would be one big conglomeration, and it would end up, from a science point of view, it isn't really that good. But from the point of view of just visual spectacularity, I'll call it, it would really be cool. So that's something we could try at some point.
I mean, I definitely want to see a star cluster with all the spectrums, but then I'm just wondering what all the kind of background stars are going to look like. Because I don't like. I don't know. Never mind.
No, it's not. You're not being, you're not being silly. I mean, I think that's a fine question to ask. Nothing wrong with that question.
No, but I mean, like when we were looking at Epsilon Lyra, obviously there were other stars around it, but we were only seeing the two. Like we weren't even picking up the two doubles that were beside them each, right?
That's correct.
Or maybe we were. It was just too close to distinguish. But like, what about all the other stars that were around? Like, how can you focus on those main two and not pick up anything? Like, I'm just wondering, besides the star cluster itself, everything around it, will it pick up? Yes or no? How's it going to look? So, I mean, a lot of people might already know this answer. I'm anticipating out loud.
No, that's okay.
So I have no idea, and I can't wait to see it. It's going to be really... It might not be useful to a scientist, but I mean...
No, but you're right. I mean, it'll be cool. Now, this is an interesting double star. Now, I don't know if you can see, but on the screen, this is a double star. Do you see it?
Is there a tiny little one to the left?
Yes, there is. This is Getty. This is Alpha Hercules, the brightest star in Hercules, and it has a very close separation, but we can see it with this particular telescope. We can see the separation pretty easily, and there it is. And the interesting thing about this, it's a yellow giant. Okay, that's what we're looking at on the right. But it's and there's also a main sequence star next to it. That is a star that's not a giant, and they have a combined spectrum of a G-type star overall, and that's pretty cool. And I like Alpha Hercules. It has a lot of interesting stuff, and now the giant star, okay, is interesting because the spectrum, as I said, looked like a G, all right, but it's actually the bright star on the right is actually an M5 supergiant, all right, and as far as the temperature on the surface of that star, it's only 3,300 degrees Kelvin. I remember our non-negative temperature scale we talked about the other night. Kelvin, there's Celsius, Kelvin, Fahrenheit, of course. And the Kelvin scale, which starts at 0 and just goes up, this star has a temperature on the surface of 3,300 degrees Kelvin. And that's a really cool star. Now, it looks yellow to us, but the designation is strange. The spectrum is G5-3 as a supergiant. That is the spectrum. But like as I said, it's kind of confusing because you see, the spectrum is odd. Has qualities of either star, but only one really wins out in the end. There's only one, one that matters. And it is a double star, and the other component, all right, is a, like I said, there's a G5 and then there's an M5. So whether I was clear or not, I'm sorry. The two stars that you're seeing are a G5 and an M5, and the stars are, of course, very close to each other in the sky for us. Okay, they're only about 4.5 arc seconds apart from us, apart from each other in the sky. But the actual stars themselves, let me give you the distance so you can figure this out. The stars themselves are 4.6 arc seconds apart from each other, and I want to get their physical. I want to get the distance. Excuse me. I don't actually see. I'm not seeing a distance parameter for this guy. Oh yeah, sorry, 360 light years. So they're 360 light years. So doing the math, we figured out 360 light years away, 4.6 arc seconds apart from each other. That means that they're separated. Those two little stars are separated by 516 astronomical units. That's pretty cool. Now that's actually, again, from that little formula that I told you about last time. That's kind of cool. So there's Russell Getty. Now, without further ado, I am going to bring us to the Eagle because you wanted to see it.
Okay, we have some more questions.
What's that?
We have some more questions coming in.
Okay.
Well, okay, and we do have some requests, but I'm gonna ask this question first since we're talking about the star.
Say again. I'm sorry. What'd you say? I missed that.
Hold on. M stars are usually thought of as red dwarfs. Can you speak of the M supergiants?
Yeah. Well, see, that's the thing with stars, and this is the weird thing. Spectral classes of stars, that is to say what they are, O, B, A, F, G, K, M. Every star that's either a giant or a subgiant or a dwarf like the sun, main sequence star, every one of these stars can be in each one of those luminosity classes, which are the dwarf, subgiant, supergiant, giant range. And it's a matter of the spectrum to tell us which one that is. So we can have an M-class supergiant, and we can have an M-class dwarf. Really, what determines M is related to temperature and its spectrum. Hang on, I gotta take a Snapple break.
Raspberry Snapple, preferred by some astronomers.
Oh, yeah. Made from the best stuff on Earth, and it keeps my voice going. So I apologize.
Possibly the universe.
Maybe even the universe. That's right. Mm-hmm. So M supergiants are interesting stars, and they're usually, when you have a supergiant like that, that's an M star. It usually means it's a star that's near the end of its life. And why is that? Because a star that size that's near the end of its life, a star that size in general, its color, if it was a massive star that was going to end up exploding in a supernova, it would be a very bright star, and it would have a blue or a white color. When you have a star that's actually near the end of its life, and it was a normal star that has bloated to massive proportions because it left the main sequence, it actually goes to something called the AGB, the asymptotic giant branch. We'll talk about that someday, not in technical terms, but to give you an idea of where stars go to when they leave the main sequence. It's like, they don't go to their room. Where do they go? I mean, they go to a place where we can see changes in their spectra, and it tells us just by observing. We see where they've gone to, and that's something that maybe we should talk about someday. I'm not sure why we got a black screen. Oh man, I just got a. It's like I've been sitting here with a black screen for a while. I am so sorry, folks. Oh man. Okay, this was a silly thing to do. I apologize. I didn't even catch it, and nobody said a word.
You know what? No, you know what? Well, it's because I'm too busy trying to focus on what you're saying, what you're explaining.
Okay.
And I wasn't sure what you're doing, and that's the thing. I try to hold back on the questions so I don't distract you from what you're doing and get you all mixed up.
That's okay. You can say you got a black screen. I mean, I'd be happy to solve that problem. That's an easy one.
I've done that so many times myself, getting caught up in what I'm saying and explaining and don't realize what's going on, but I'm a lot less professional than you, so.
No, I was just.
I'll try to keep my eye out for that next time.
It's just not a big deal. Okay, 10 seconds at 12,800 ISO, and we're gonna see what we've got. The humidity is a little bit higher tonight than last night, and it does make a difference. It does make a difference. Let's go back. Well, this is the Eagle, and you can see the pillars, but I do have to do a little focus work. I can see that. So I'm going to come out of here. I'm going to go into a magnified view here. Find that's all I want. Where am I going here? I want this. That's what I want. Okay. Alright, and now let me focus. Right off the bat, you can see that it's bouncing around. See how the stars look like they're all like shimmery? That's because this is lower to the horizon. And that's part of the problem. Okay. See, you can see it right here, how it dances around when I go out of focus with them. The stars dance around, and that's because, you know, it's not higher in the sky.
Well, see, I had a crazy question earlier, and I don't know, for some reason I forgot it. And it's, I mean, I have a feeling I know the answer already, but...
Okay. What is it? What was the question?
Can stars actually fall out of the sky?
You know, that little bit of mythology came from the fact that people would often say, oh, look, a shooting star or a falling star. And you thought, you know, you think, well, that's a big, you know, that's a big giant thing falling out of the sky. As a kid, when someone said, look, a falling star, I would think, wow, the Earth's going to get destroyed, because there's no star that's, you know, an average typical star we could see in the sky that is the size of the Earth. There are stars that are the size of Manhattan Island, by the way, and those are very, very dense, odd, exotic stars with very, very dense material, and they could be only, you know, a few tens of miles across, but those aren't stars that are doing normal processes. They're the end result of a star's life. So, you know, but most stars are the size of the sun, or a little smaller, or much, much, much bigger. You know, I mean, there are stars out there that are so big that if you put them right here in our solar system, where the sun is, you would end up having a star that would go all the way out almost to the planet Jupiter in its size and diameter. That's massive. I mean, absolutely, stupendously, colossal, and massive. Really, really incredible. Let's see here.
Well, I just want to tell you where that crazy question came from, because yesterday when you were talking about the moon, and you were talking about, like, things that hit it were, like, they were settling on the far side of the moon because they were cooling down, right?
Yep.
And then some of the stars we were looking at earlier had a lot of blue, but then the ones that were closer to us had less blue. So I'm thinking that's because they're cooling down, right? We see more red if they're cooling, right?
Yeah, no, that's see, the problem with that is that you can't you can't put those two things in the same category, because those don't work. That bit of
star, one's like an asteroid, or
well, I mean, one is bombardment in the early solar system with particles of silicate materials, you know, and molten balls of silicate materials and iron, and the other is a star, which is a hot plasma, construct that's very, very different from a planet. So the science of the two overlaps in that one can create the elements for the other to be fabricated. However, that's where it ends. Then planetary science is not star science, and stellar sciences, that's very, very different. To be a stellar scientist, you have to be a chemist, you have to be a a mathematician, you have to be a physicist. To be a planetary scientist, you have to be a geologist, an environmental sciences guy, and a physicist and a mathematician. So I mean, they're equally challenging disciplines, but they're very different morphologies and very different they're very different, processes, I should say, that drive what makes a planet cool down, what makes a star change. I mean, we saw Tabby Star one night, remember? And we were looking at a star that's been dimming, for instance. The light has been dimming for about 100 years. And that's incredible. I mean, now, planets don't dim, see? So a star is intrinsically different from a planet in that regard. A star is made of material, like solid material. A star is not. A star is made of gas, and at its core, the gas is compacted very small and tight in there because of the weight of the overlying material. Sometimes hundreds of thousands, if not millions of miles out from the core. And so the gas is very hot and dense in there, and so that's what causes the star to basically be born in a cloud of gas and dust. Once the pressure reaches a certain place, then the star literally turns on, and all of a sudden it's like, this star just begins burning and infusing hydrogen into helium. A spontaneous explosion that will last billions of years. I mean, that's just incredible. By the way, M16, the images are not coming out very well, and the reason is because the moon is up, and the moon is sort of on that side of the sky. So, trying to look at nebulae today until the moon sets is just not a good idea. So we'll have
there was a request. Okay. Can we get a close-up of a pulsar? And then that was from Monkey. And then Ted said, "Don't pulsars pulse radio signals, not light, or is it both?" And then Daryl suggested we could faintly see the pulsar in the Crab Nebula, but we'd have to wait until the fall or winter.
He's right.
And that's actually pulsing 30 times a second.
Yeah, so we wouldn't see it actually pulse unless we actually took a video of it, and they have, and did it with a high-speed, high-sensitivity camera. Gee, where can we find one of those? Oh, wait, I got one. And maybe we can actually see the Crab pulsar doing its thing, but we need a high magnification. And I might not have that ability with the telescope to do that because of the magnification required. We probably need a big, professional instrument that's, a meter in size before, in the mirror size, to try and get that. But I'd certainly try it. I would certainly try it. You know what I mean? I would certainly try that. All right, let me.
And there's a lot of discussion going on for the upcoming eclipse.
Yes.
Ted's looking for advice on whipping up a homemade filter to watch, and Daryl is telling him,
no, no, do it. No,
the eyes. Be careful with the eyes.
Yeah. No homemade filters.
Homemade filters.
It's you got enough time to get yourself a professional solar filter, even if it's just one that you can hold up the solar filter, the sunglasses, basically, not sunglasses, but solar glasses. Welding glasses, not good enough. I know you think it might be, because you say, well, after all, it stops the arcs from, from the welding, but welder's glass is not sufficient because welder's glass is not consistent, and that can be a problem as well. And even though you might hear people saying it, I absolutely wouldn't trust it, and I never have. I've always used my, my position as an astronomer with different organizations to encourage people to get the proper gear for observing something like an eclipse.
Yeah, because I know there are people in here giving different advice.
Yep.
I'll definitely protect the eyes and everything, but if you had any other suggestions.
Well, I did a I did a demonstration routinely with people that would come up to use the 14-inch telescope that I was, in charge of at a science institution, and I would show them. I would say, "Here, let's point it at the sun." I would point the telescope at the sun. Of course, everybody's in the observatory with me, and I would shine the sunlight down through the the eyepiece and have it come out on a board, and people would see this. It's called eyepiece. It's projection basically. It shows on a flat plate that's attached to the back of the scope, and they could see the whole sun. But that's only in the visible light. And they said, why can't we just look at it with our eye? I had someone ask me that question. I said, oh, you want to see? And I took a pencil out of my pocket, a pencil, and I passed it up near the eyepiece where the light was coming out. I just passed it right in front of that little area, that little aperture where the light was coming out. And the pencil started on fire.
No.
Oh, yeah.
Oh my god.
Yeah.
I thought you were gonna say it. I'm like, there's no way. I thought maybe it would have smoked a little, and I still wouldn't have bought that.
No, it caught on fire. And you gotta remember, it was a 14-inch telescope, so all that light is concentrating down to a little tiny aperture that's about a quarter-inch in diameter, and so it might as well have been a death ray, but it was actually dispersing. And going out 3 or 4 feet back from the telescope onto the cardboard where people could see it, And if you put your hand even on the disk of the sun that was on that cardboard, it was warm. So when I showed that, that was kind of a new awakening for a lot of people. And they realized, yeah, I don't think we're gonna be playing with these at all. I don't think we're gonna be doing that. No, we're gonna get the right things. And that really drove home the entire issue, and no one ever abused it after that.
I would love to get that caught on film. If it didn't destroy the telescope, that is.
No. See, the telescope was battle hardened and made for doing that kind of thing.
Yeah. But just like, and you can't do it until the actual eclipse. So you can't put it out as a disclaimer, like, please pay attention. Do not just look up.
Well,
that's. Please, everyone listening, take that as a lesson. Do not forget the story. Share it with other people.
Yeah, they'll be fine. You know why?
Wow.
Because they're smart. They really are. And I gotta tell you,
people in this chat are, but tell people that in your community that may not be.
Well, that's true. That's true. We might not have that.
No, well,
overall smarts.
It's such a not such a rarity, but I mean, it's a long time in between, and what do you want to do? You want to look up and see it with your own eyes.
Yeah, no, I'm actually gonna be, I think, in Nashville for the eclipse. I'm in Connecticut. I'm gonna be going down to Nashville because Keith and I and Paul and a bunch of other people are actually going down, and Keith actually arranged for us to, I think, be on top of a skyscraper in Nashville during the eclipse. And if it's a nice day, we're gonna see it'll be great. But if it's not a good day, then we have a swath of distance we can go southeast or northwest by about 90 miles or so in order to actually see if we can see this eclipse, So we might have to outrun a front or something like that, but or not, or it might be nice, might be clear. We shall see.
And that's the 21st of August.
Yeah.
What time is the best viewing?
Well,
the gap.
21st of August, remember, it's only a 20-mile wide path from northwestern United States to the southeastern United States. And you consult the eclipse path stuff that's out there, and you can see it. But it's really neat, and when you go to see the eclipse, one of the things that you'll like, I think, the most is that that you will actually be able to see if you're in the path of totality. As soon as the sun is covered by the moon, you'll see some of the brighter stars that are in the side of the sky the sun's in. And so it's actually pretty cool. 'Cause suddenly it's night for just a couple minutes, and then it's gone that fast. And sometimes people get pretty disoriented with the fact that there's this big shadow over them, and there's these bands, almost like interference patterns, that precede the eclipse that goes zipping by and across the countryside, and they're just they're just parts of the shadow that are heading to you, the penumbra of the shadow reaching you. And when it hits you, you actually, it feels weird because you can actually see the what's the word? It actually it's a palpable feeling, a palpable sensation that it's actually something's going on. You actually feel the darkness approaching. It's really, really strange.
When's the last time one of these happened? Because I'm sure I was outside at like 2 in the afternoon in high school,
Yeah,
which wasn't that long ago, and that there was a solar eclipse, and I don't think it was a full one, but it did. It seemed like it was midnight at like 2 in the afternoon. It was crazy.
Yeah, I remember being in school and they wouldn't let us out to see the eclipse, we just sat in there as it got dark. Street lights went on. Okay. Started to hear bugs and crickets, and then all of a sudden they went away, and then all of a sudden it's back to being daytime again. It was actually
I don't
very,
remember
very cool.
hearing any crickets or anything, but see, these are all things I'm definitely going to be looking out for.
Yeah, no, do that.
Weeks.
It's going to be really cool. Very cool indeed. Now, of course, let me do something here now. I'm actually not been sitting here just, goofing off. I'm actually been looking for something to show you guys. And we're going to go to this. That's where I want to go. This is a this is a little open cluster. It's right up high. We should be able to see it. I think we should be able to see it. Hey, get on there. And pardon me here. We're gonna figure out where my leg's going. All right. Alright, let's see what we got. So, what we're looking at is a little open cluster, and it's an interesting little cluster that's it's got just a few stars, not many, and I'm gonna just give you the information on this so you can have an idea. It's about 1,600 light years away, so it's actually pretty good distance, and it's about 10 light years across, just so you know. All right, so let's take a photograph. Let's do a photo at 6,400 for 5 seconds, and here we go. So again, 1,600 light years away, and it's about 10 light years across. Each of these stars is now you can think of these open clusters like this as not being flat, okay, to you. They're actually there's some kind of distribution. Maybe some are farther, some are closer, so maybe some are a little bit more more like say a spherical distribution. Some are not, but this is a nice little cluster to enjoy and look at. You notice all the stars are about the same brightness. That's typical of some of these clusters. Pretty cool. Now, anybody have any questions in chat at the moment?
Not at the moment.
Good. No, I'm only kidding.
Oh, they'll throw them in as they come.
Yep.
Again, a lot of discussion is still about the eclipse coming up, and Daryl saying it's going to be the most photographed event in history. I'm sure. I'm wondering how many people are going to be streaming it. Everyone has to be here, of course.
Oh yeah. No
so
doubt.
if you haven't hit that bell, for goodness sakes, hit it now.
Yeah, please. Come on, guys.
I think most of them do have it.
Mm-hmm.
And saying Walmart might be offering eclipse glasses, not sunglasses, but like sun viewing eclipse.
Yeah, maybe. Maybe.
And I know that Daryl's putting different links in the I think Amazon was one, Orion, maybe Orion.com.
Mm-hmm.
I'm not sure. So yeah, I don't know these sites myself, so I don't want to plug anything if I'm not sure. But that's why I said
that's
to you,
fair.
if you know anywhere for sure, that's
Well, I mean, you can always get some kind of viewing glasses from Edmund Scientific. You can also get them from Walmart and other places, but you know, you gotta trust them. By the way, on the screen right now, I have a really cool double star. It's actually Theta Serpentis, Theta 1 and Theta 2, and it has a name. It's called Alya, A-L-Y-A. And Alya is a fascinating double star because if you notice, you see there's two nearly identical bright components that you see, and I'm going to center them for you and go over to them like that. See that? And it's a really pretty double star. I mean, and I want you to see that because Alya is it's a beautiful star to see. All right, now let me get off of there and go here. Oops, I didn't want to go there. My apologies. I'm going to go here. That's what I want. Okay.
Okay, Ted wants to know what the two stars at the bottom are.
I think he's talking about these, right?
Probably. Well, they're centered now, yeah.
Yeah, this is Alya. These are the two components of Alya. It's Theta 1 and Theta 2 Serpentis. And you know, we designate stars with Greek alphabet names: Alpha, Beta, Gamma, Delta, Epsilon, Zeta, Eta, Theta, Iota, Kappa, Lambda, Mu, Nu, Xi, Omicron, Pi, Rho, Sigma, Tau, Upsilon, Phi, Keep, Psi, Omega. That's the Greek alphabet. But if there's two stars like really close to each other, and the same brightness, well then you can't have one, you know, and they're in order of brightness. So alpha's the brightest and omega's the dimmest. Well, if you have two that are the same size, same brightness, and they're right near each other, you may want to call them by the same Greek alphabet name, but with a number 1 or number 2. So this is Theta 1 and Theta 2. And they do that, especially when a star like Alya, which is fairly bright, is in a constellation. So, and you can see that it's really something else. It's really quite a beautiful star. I'm going to try and change the focus a bit here.
Okay, now I'm not sure if the answer was in that explanation or not. Jerry wants to know what class stars are these in the cluster.
Oh, you mean okay.
Delta?
You mean these guys here? These two?
Yeah. Well, I don't know. I don't know. The question came in when we were looking at all of them before we zoomed in, so I'm not sure.
Oh.
What class stars are these in this
I'll give you a clue. I'll give you a clue here. Let's defocus a little. Do a little trick. And I don't have the spectrum thing on yet, so
I want to see the spectrum of all of the stars, not just these two.
I know you do. I know you do, and we can't do that yet, unfortunately. All right, but let me just bring these. It looks like headlights coming at us from a distance, doesn't it?
Or cat's eyes. Yeah.
Or that, yeah. Okay, look at the color. What might you suspect by looking at the color?
I'm waiting.
Anyone in chat? What might you suspect?
Okay, what's the question?
Well, the question is, what spectral class do you think they are?
Oh, okay.
Look at the color. The color is sort of a bluish white. Almost white.
I have a guess, but I'll wait until
Okay.
people in. I put the question in. They should have heard your question by now. I'll wait until some.
All right.
Oh, I think I'm right though because you're not. Someone agreed with me for a second and then changed their mind, so now I'm second guessing myself.
Okay. Well, let me see here. Let me see if I could just take a couple of photos here. I can see that my camera battery is going to die, and I have plenty. I made sure that I had plenty of charged batteries for tonight.
And the way to remember the classes is the little mnemonic device of O be a fine guy, kiss me.
Yep.
Or O be a fine girl, kiss me, whatever your preference is. So it's
Yep.
O B A F G K M.
Correct.
So those are your options. So one of those seven
That's right.
are the option.
Yeah, and these stars truly are that spectral type. There's no trick question here. Or spectral class anyway. So this is going to be cool if you can figure it out. So I will let that go for now until someone comes up with an answer. We see the stars now on the screen. That's what we're looking at. And before the camera dies fully, I'm going to just get another battery out of my battery drawer. Here we go. And okay, the camera's going off now, and I'm going to change the battery. When I come on, it'll be right back where it was without fail. Okay. There we go. Battery's in, locked, closed, back on, and we should see. And there we go. We're back. So, any takers?
Okay. Daryl at first said A, then switched to B. SP is saying he's going to cheat and say B. But I thought it was A as well. That was my first guess because Vega is A and Vega is blue. But Daryl's saying it's blue-white, and that's why I think he went with B. So.
Okay. Well, these stars are A5. So right in the middle of the A spectrum. Now, when you look at it, okay, you can't listen to me if if I say something that you may interpret to be sort of a hint, and there was no hint. I said they look blue-white, right? But they're actually they're A stars. Both A5s. And you look at the predominant color. The predominant color is white. If we looked at the spectrum, we would see equal blue, equal green, equal red. In a B star, we'd see more blue than green or red, but there'd be green and red in the spectrum, just a lot less. But these are just beautiful stars, aren't they? And look at those little gems sitting right out there, just waiting to be seen. And the interesting, what I like about these stars is that, okay, these stars, all right, are actually like 4.6 magnitude, and it's not bad. And they're 155 light years away, and you can see with your eye down to like magnitude 5, typically. And mag 4 in a light polluted area, 3 in a more light polluted, and sometimes no stars in the city, but you can. But these are 155 light years away, and they're 22.3 arc seconds apart, and that separation puts them at 1,060 astronomical units apart from each other. Isn't that incredible? 1,060, and that's really neat. I like that. Now, the interesting thing about these stars is they have a temperature around 8,200 degrees Kelvin on their surfaces, and they're each they're slightly different from each other, although they're still both A5s. They're 18 and 13 suns in diameter. So one's 18 times the size of the sun, and one's 13 times the size of the sun. If you think about that, that is just really cool. Actually, sorry, let me apologize. Their luminosities, their brightnesses are 18 and 13 times, respectively, over the suns. And as far as their diameters, they're about 3 and just about 3 times the size of the sun in diameter. And that's still big. That's really big. And they're both about twice the mass of the sun. So they're big stuns, and they're also they are rotating very rapidly. So and there's a certain class of star called a rapid rotator, and these are them. Okay, these are rapid rotators, and so they're not round. They don't look spherical. They actually are oblate and kind of like squashed and looking, you know, because they rotate so fast. Really cool. Now, there's also um, another star that you can see in the image. Okay, remember these are separated by 22.3 degrees. All right. However, there's a third star that's bound to them gravitationally, and that star is actually a yellow G-type star. Now, with the camera, you really can't see the difference, okay, in the color so much. But it's actually a little bit fainter. It's a magnitude 6.7 as opposed to 4.5 for these guys, 4.6 for these guys. And it's actually, you know, it looks like it's part of the system, but it's probably not. But you know, it looks like it's gravitationally bound. We're not sure. But we have to figure out, you know, what the star is doing, where its motion is, because again, all stars move through the sky, and we can detect that year to year. We measure that. That's something called proper motion of a star when it's moving in the sky, and we're watching it move in its orbit around the galaxy is what we're seeing. So there's some really interesting little things here that are just so much fun to explore. And you know, I remember looking at this double star when I was a kid with my refractor telescope, primarily because it was one of the only stars that I could actually separate in with that small thing, and it was beautiful. And I just remember looking at it and thinking, wow, those two stars. If I was there in that solar system with those stars, can you imagine what that must sound like? Loud roaring of all these stars, big stars. We didn't even know at that time how much bigger than the sun they were. But in time, we learned all these things, and I just find it fascinating, and I can't get enough of it. Let me tell you, especially tonight. It's really beautiful out. So now, I think what I want to do is I'd like to take us to another object. Again, the moon is still out, but it doesn't matter. And I've been using a little bit of a different approach today for getting you to see some things. And one of the things I'm going to do is I want to take you to, in the absence of any requests, I want to take you to something that has been like a favorite of mine. Okay. Alright, let's try this. Okay, we're gonna go here now.
And I think I figured out why we couldn't get hold of Keith earlier.
Oh, really?
Yeah.
Why is that?
It's Sunday. He's probably watching Game of Thrones.
Oh. Well, no, it should be over by now. No?
Probably.
Yeah, I would think
Maybe
so.
he went to bed after.
No way.
Maybe he's vlogging about it.
You know, maybe he is. I admit I was watching Game of Thrones.
Really?
Yeah, I was. Alright, I'm going to take a photo here. I just want to show you something here. This will be I'll do a 5 seconds at 8,000 ASA. Might be a little bright with the moon. Cause it's kind of near the moon. Not near the moon, but the moon is in the vicinity. Alright, good. not that bad. Now remember I talked about proper motion? You know, the speed of the stars against the, you know, in the sky. And sometimes we can see them moving, you know, we can also see them moving, we can see the stars move against other stars. And that's what we're looking at, or could look at in this case. Let me zoom in here. Okay, I want to find it. Hang on. I might not. Let me go to this mode. I'm kind of stuck on the other side of the pier, so I can't really see the screen right now. Okay. Alright, so there it is. Let me just go over there now that I see where I'm going. That little tiny faint star right in the center of the view is Barnard's star. It's one of the fastest moving stars that we've ever had or ever seen. You literally can measure the movement of it over the course of a few years. And I'm doing a 10-second exposure of it here. Okay, that's the moon. That was a moon exposure. Shouldn't have done that. Let's go down to 8,000 at 10 seconds.
Now, why have I heard of Barnard's star before?
Because Barnard's star is one of the fastest moving stars we've seen. It's close to us. You know, Barnard's star is not that far away. It's actually it's only oh gosh, it's literally just a little bit farther than Alpha Centauri. It's 5.96 light years away. You know, and that means that Barnard's star is actually in a category by itself. You know, it's very close. All right, now let me do this and this. There we go. There's little Barnard's star. Say hello. So Barnard's star is, you know, a reddish star, as you can see, and you know it's only 5.96 light years away, yes, but it's also a very interesting star. It actually has it's an M4 dwarf basically, and it's an orangey red star, and it has this incredible motion. And that means it's because it's close to us and it's actually swiftly moving. So it's you know, it has a 3,000 degree surface temperature. That's Kelvin. Every temperature is in Kelvin. And the luminosity that it has, it's only 5.96 light years away. And Alpha Centauri is you know, a G star, kind of like the Sun, and the Alpha Centauri primary component. There's three actually, A, B, and Proxima. A is the same kind of star as the Sun, and you would think that a star that's only slightly further away than Alpha Centauri would be a star that you should be able to see with your eye, because Alpha Centauri certainly is. Well, no, this star is actually only 0.00035 times the brightness of the Sun. It's literally a mere fraction, you know. I'm sorry, 0.0035. I apologize. I meant to say 3.5 thousandths of the luminosity of the Sun. I'm sorry. God, I'm sorry, guys. I am tired, and you know, I guess I didn't get enough sleep because when I saw how clear it was, I was thinking, oh, I gotta get back outside. So I was trying to prepare stuff all day. it's literally the diameter of the star is only 3.5 thousandths that of the sun. Is really incredible. And it's only 17% the mass of the sun, so it's a really, really small star. Most of these red dwarfs are, though, see, and that's the thing. These red M-class dwarfs are very, very ultra cool, very small, and I mentioned this before, you can't see a single one with your eyes, and they're the most plentiful star in the entire universe. There's more M stars than any other kind, and it stands to reason that more planets exist around M stars than any other kind, and that's because they're the most plentiful star. So it's kind of cool that there's this going on with Barnard's star, and here it is. You're looking at the star right in front of you.
Daryl wants to know where specifically in the sky the star is.
Sure. Yeah, Barnard's star is in a constellation called Ophiuchus, all right, or Ophiuchus, depending how you pronounce it, and that's spelled Ophiuchus, Ophiuchus or Ophiuchus, Ophiuchus, 3 different pronunciations. It's a constellation that begins with the letter O. Just remember that. And when you look at it, you'll say, "Oh yeah, that was at Ophiuchus something or other that he said," and it's in Ophiuchus. So, and Barnard's star is right now it's actually pretty high in the sky relatively. So it's not bad.
Can you compare its size to Jupiter? Is it bigger, smaller?
Oh, that's interesting. Well, the Barnard star is only 20% of the size of the sun. Okay, so if you figure Jupiter's diameter at is it 88,000 miles in diameter, and the sun is 864,000. Just do 0.2 times 864,000, and that gives you a diameter in miles for Barnard star. So when you do that, you compare it to the diameter of Jupiter, and you'll see exactly what it is. That's how you would do it. I'm standing here with an iPad in my hand. I can't do that in my head, but I could actually.
I was gonna say, yeah, you could. You just don't want to because you just finished saying you were tired. So
yeah.
No math on a Sunday night, not astronomical measurements anyway.
Oh, but see, that's the thing. I just never stop doing that stuff. I don't. I just like thinking about all these mysterious things. I just never stop thinking about them. I just don't. I don't know what's wrong with me.
It's called being fascinated.
Yeah, I guess that's probably what it is. I am. I am very fascinated by a lot of these things.
I totally get that. I'm like that too. It's just that's why I need channels like this, because I don't have the basics to ask the proper questions. Like when I was talking about like can a star fall like the way the asteroids would fall on the other side of the moon when they cooled.
Yeah.
Well, they're not compatible questions. They're not. They don't mix, right?
Correct.
But I don't know that, right? So.
Well, you do now.
Well, I do now. Well, exactly. Thanks to you, right? But
I always said there's no stupid question. You know that.
And I think chat's already picking up on it. I do. Slowly but surely, I can only take in so much a night, but I am picking up on little things, and I think the questions are getting better.
Actually, they are.
Not the nonsense they give you off air, but I mean, I think they're getting a little better.
I think you've been actually you've come a long way, and I've listened to some very intelligent commentary in the chat, which was just amazing. You've got
chat's
a lot of
incredible.
Yeah, they got a lot of smart people out there, and I'm glad to see them come. To my stream. I just I'm humbled by it, because I think that it's wonderful to see people come to my stream who actually have brains and thinking, and don't just want to just be entertained by the silly guy with the telescope. So I love it.
And you know what? I mean, I don't know if I should say it because I don't want to jinx it, but I think at the very, very start we may have had 2 trolls in every single stream, I can't remember. I really cannot remember the last time I had to ban anyone. Because people, like, I don't know. I think you just win them over, even if they wanted to be trolls. It's just too incredible, and they're just too stunned to be jerks, you know. And they're like, "Wow, what did I stumble into? I'm gonna stay," you know. So
you're kind of exaggerating just a little bit there. I think that it comes down to the fact that there's certain streams you can kind of do that in, and I think there's other streams where, you know, they realize, well, everyone's here to really learn a few things. Or actually, you know, it's like walking into a college class and just like doing a silly dance up in front of everybody. I mean, you tend not to want to do that, but you might do it in like an elementary school. You might do it in sort of like kindergarten. You might walk by and go, you know, looking, make up faces or whatever. But you wouldn't do that in a college class. So there's a different mentality, there's different people, different involvement, and so they recognize that, and they realize what might be funny and what won't be funny. And what won't be funny is someone who comes in and just does something silly like that, and, you know, they'll just end up being the laughing stock because they're the idiots. And they kind of, I think, I could be wrong, but I think they recognize that. So that's all. I don't find it to be you know I don't find it to be a problem. I just think that, you know, I expect trolls, like, you know, here. I expect them anywhere. Maybe I just got lucky, you know.
Wow.
Maybe just got lucky. Maybe not.
I don't know. I think, well, maybe luck, but I think even the potential for trolls, I think you win them over because in their mind, it's live, it's astronomy. How we haven't attracted more flat earthers is beyond me. But I mean, this is what they do. They have no lives, and they want to disturb people and, you know, get attention for a minute, but they will be banned automatically. I mean, that's a given, but I mean, it just doesn't happen here. People are so impressed and I think so appreciative of what you're doing that they don't want to take the chance of being banned. They don't even want to joke because it's too important. It's too good.
There's a number of people out there that have been part of this for a while who recognize it. If they say something a little bit lewd or whatever, you know, they're not going to get banned right away because, you know, that kind of thing. Hang on, I'm just going to go to another object now, another double star I want to show you, because it's really pretty. Oh, good. I thought I was going to run out of dome to spin, but I'm not. Okay, let's see what we got. There it is. Wow, that's pretty. Looks like headlights going the wrong way. Okay, so this star right here is a really pretty one. It looks kind of like the other one, didn't it? Except there's a big difference here. And I'll tell you in a sec, once I get them all lined up. Okay. Alright, so this star here that we're looking at is actually fairly famous. It's called 61 Cygni. And it's a very widely separated double star. And if we look, and if we went into this star and looked at the spectrum, you would see that the spectrum of this star will show that these two stars are actually very orange. And we can actually maybe show that, actually. I'm going to try and do this. Let me just hop out of this for a second. And I want to try and see if I can show you the orange nature of these stars. These are actually, these are 2K class dwarfs. So these are main sequence stars. And they're fusing hydrogen into helium in the normal way. And they're just about 11 light years away. And they're separated by 31.7 arc seconds. And that puts the distance between them at 126 astronomical units. Yeah, I do a little homework ahead of time. What can I say, guys? I just gotta do it, you know. So that means that these particular stars are really neat in the following way. At 126 astronomical units, it's not 1,060 like the last last double like this we looked at, it's only 126 AU. So these go around each other every 650 years. So while the Druids were doing their thing, and while Stonehenge was being built earlier, and while castles were being laid siege to here on planet Earth, these stars were just slowly orbiting each other in their continual cosmic dance. I think looking at things in terms of the time is really awesome. And that's what we're seeing here. Now let me just come in on this a little bit right now. I want to see one thing. Okay.
And it's again something, I don't know. It's just things you don't really think about. Like, you think about stars and what are they and what are planets and stuff, but I don't know. Me anyway.
No, that's fair.
You don't really think of it as I'm taking a snapshot back in time.
Well, that's what I'm
it's
saying,
just,
Yeah. That's what I do. So
yeah.
This is the star. No, but again, they're only 100 and like I said, as far as their distance, the distance these stars are, at these distance of like, they're only from us. They're only 11.4 light years away. So 11 years ago, the light left the stars that we see there. Okay, but what I'm saying is, in their orbits, they've been orbiting each other and just pirouetting around each other for centuries and millennia. And while the whole history of the Earth was unfolding, those stars were just quietly circling each other out there. And had the folks that made Stonehenge been able to look at this star, 61 Cygni, they would have noticed that the stars were actually kind of in a different arrangement. They were kind of, the angle that they were looking at wouldn't be like this, where one's to the lower left, one's to the upper right. Maybe they were side by side at that point in their orbit. So, our history goes on while these stars, their history's been going on for billions and billions of years. So I just think it's pretty cool to think about things in terms of that. This is actually these stars are actually basically, this star system is pretty much the one of the most important stars in the sky besides Barnard's star. In 1792, Giuseppe Piazzi actually called this the flying star. And it was really done. He did that because basically the stars are moving together through space at a very fast, proper motion. Again, there's that word, that phrase, proper motion. The proper motion of these stars actually make them have, it makes them have a different position over millennia. So they're going around each other, but they're also traveling through the galaxy at a good enough speed, and at only 11 light years away, they're close enough for us to actually have see the stars moving against the background of farther stars. And it was noticed all the way back in the 1790s. Can you believe it? And that's really cool. And so it's a very important pair of stars. And the first star in 61 Cygni is actually, a kind of a, it's a K5 basically, so it's an orangey red, when it's a little smaller than the sun. So it's pretty cool. And then the second one is a similar, it's a K7. All right, so there's K5s and K7. Like Space Station K7, right? That's a Star Trek reference. I apologize.
A lot of people in chat love it, but I don't get it.
And so the nice thing is when we look at this binary system, one of the things that's really cool is that these stars sort of have a magnetic cycle like our sun. Our sun, every 11 years, its magnetic field gets knotted up, and we get more sunspots on our sun every 11 years. And they've detected a similar cycle on these stars. Now, the other thing that's interesting is circling both stars is a dust disk. Now, what does that mean? That means we might be seeing a planetary system that's coming up or is going to be forming there over the next several million years. And that's what's cool about the universe. We always see planets in formation, and we see planets that have survived the death of their star. We see planets that are in their full maturity, like our own, and everything in between. And that's what happens in the universe. We see that only a few million years after the start of the universe, that's when the first planets were formed. And it's been an ongoing thing. So, the Earth is, like I said, you've heard this before, the Earth is 4.6 billion years old. The universe is 13.8. 2/3 of the life of the universe went by before the Earth even formed. So, there could have been planets that came and went, and civilizations even that came and went. Or civilizations that came and stayed, okay, in the time before the Earth was actually here. And now, we're here now, and we look around and we say, well, I can't, man, there's no aliens, there's no life elsewhere, there's no intelligent life. Who are we to make that decision? We can't make that judgment. We haven't been here long enough to even be considered a true member in the universe. We've only been here for 50 to 60,000 written history years. In terms of that, and as I said before, just over 4 million if you want to count the first time we started walking with bipedalism and with Lucy, the Australopithecus. And that was over 4.2 million years ago or so. So here we have 61 Cygni, and while Lucy was walking around in 4.2 million years ago, these stars were still circling each other. However, they were not in the same place. Because they're so close, they were a lot farther away, and they got a lot closer and will get farther away again as they continue to pass us by. So these are kind of interlopers to our local area of space, that is, distance within 25 light years or so. And they're going to head right on out because they're moving faster than we are. So it's pretty cool. And I like, if you look, you look at the universe and you see stars in the sky. You have to remember, everything is moving. Everything is moving. Everything's in motion. Nothing is still. Every star you see in this photo, every single star you see in this photo is moving. Now, some of the stars are going in a similar direction, some are going in different directions, because some are on a little more inclined orbits around the galaxy than others, but they're predominantly in a disk. So this is cool. 61 Cygni is a beautiful double star, and if it looks like this to your eye, you can imagine what it looks like, when you actually, if you could actually go there and see it. And then, of course, in a nice telescope like this one, we could actually do some really nice things and get some beautiful photos. Like if I go, say, and do a 15 seconds at 6400. Let's try that. It's probably gonna be about the same as what we just saw, but I wanna just take the picture and see what we get. So 15 seconds at 6400 ISO sensitivity, and here we come.
We do have some questions coming in as well. They're kind of opinion questions.
Okay.
Tron says, it's an accepted theory that nothing can escape singularity, not even light. Yet a while back something was observed exiting one. Mark, what are your thoughts on this?
I'm not sure if what he's talking about is the fact that we could see at the singularity high energy magnetic fields that actually allow us to actually see where the black hole is. I mean, we've actually singularity and black hole, he's talking about black holes, so you know that. And so when we talk about the singularity having something escape from it, nothing will get out of a singularity, because light is X-rays, radio waves, infrared energy, ultraviolet light. Okay, ultraviolet energy. That's all. Those are all. When they say nothing, not even light can escape it. Light, in the broadest sense of the term, means everything in the electromagnetic spectrum, and that includes X-rays, etc. So, so nothing like that escaped. But we did probably see magnetic fields, high-intensity magnetic fields at the surface of the singularity. Now that surface is at the point called the event horizon.
I knew that.
Oh yes, it was an interesting movie too. A little weird, but Event Horizon was a fun movie actually. I think it had Sam Neill in it, but anyway, at the event horizon, once you pass that event horizon, then that's it. You are forever trapped inside this black hole, or
pulled out to the other side.
Or you make your way...
Like stretched out?
Well, you would be, that's the thing. Okay, any corporeal being would be... and this is kind of hard to follow, but because you can't imagine this. Anything that enters a black hole like that, like a being like us, the differential gravitational pull at your feet, if you're going in feet first, would be so strong compared to at your head, because the gradient, that is the change in the gravitational force, is so steep at a certain point entering the singularity that your feet would be stretched out from your body and your torso and your head, and you would be stretched out into like an infinitely long ribbon. Okay, if you can imagine. Now, certainly in real life you could never survive that stretching. You would of course break apart, but technically, if you were a blob of energy going in there, you would actually literally be stretched out to the size of an infinitely long little ribbon. It's a fascinating topic to talk about, to be honest, but I don't think that anybody really wants to try and find out.
But I mean, like, well, that's the thing, because I did read some kind of article a year ago saying how it would just, like your body would be stretched.
Yeah, exactly right.
Not like you're being sucked through, but like your body would be stretched, right?
Yeah.
But even if they brought a camera in, it's not like there is no test that they can even come up with. Like, how would you even know? How could you even prove it?
Yeah, well, that's
like what could you put through to see what happens on the other side to have anything come back? You know what I mean? Like,
I do.
Once you get to the event horizon, what do you do? Like,
well, it's not like you can report back, because as soon as you try to send something back after you get in, let's be fair, nothing's gonna be coming back.
Exactly. So I mean, I don't know. Would you consider that a paradox even? Because the best theory is you get stretched out into not an infinitely long ribbon.
Well,
would it be infinite?
Yeah, I mean that's the classic discussion. Is you would be stretched into an infinitely long little ribbon.
But there's like 5 different categories of infinity. So I mean, if I'm 5'4" and I go in with someone who's 6'2", how are our infinite ribbons going to be infinite?
Well, of course, you that's the whole point. Like I said, you'd break apart because you would stretch, obviously, to a certain point, maybe a couple inches, and then you rip apart. It's a nasty business, Calculating black hole death is just not my thing, but I think it is kind of cool, to consider that that is an interesting factoid we have to deal with, right? We have to deal with black holes and things like that. And if you think about it, black hole is the location of the most exotic matter almost that we know of. And we can't even really say what the black hole is actually composed of, in a sense. We don't even really know, do we? We know that it's a collapsed star, but it's a star that's collapsed so much so that it's actually formed an infinitely small point called a singularity. And it's like, how can that possibly be? You know, there's so many things that go against intuition and understanding when we talk about black holes. I mean, at some point we should have a little discussion. Again, on a cloudy night stream, we should have a little discussion about black holes and go through, you know, how it's theorized they form and so forth, because that would really be kind of cool. I think people would enjoy that.
Oh, I'm sure of it.
We're back.
I mean, like, there's stuff in the universe that's missing, right?
In a sense, yeah.
In a sense.
There's mass. There's missing mass. And you might say, well, you want to say, I think you want to say, is it inside the black hole?
Is it on the other side? Of course it is.
Well, I mean, we don't know the answers.
Or whatever caused the black hole had that material, that matter, that whatever it is.
Yeah.
And now it's gone.
And
so I wanted to know if there was another star system that existed billions of years before us and disappeared, like collapsed on itself, or I don't know, the star went supernova, and I don't know, and ripped apart all the exoplanets. Like, would we even know? How would we even know? Can we test for that? Have we found sections of the universe where we think the star system may have been and was destroyed? What's there now?
I don't know that we can detect that. We don't have the ability to detect, you know, what was. We only can detect what is, and that's not even too good. You know, we're okay with it, but we're not very good at it. You know, we're not very good at knowing what the universe is. We're not very good at knowing what the universe is really made of. You know, we know 4% of our universe. 4%. And in that, with that 4% knowledge, we actually put rovers on Mars, people on the moon. Okay, so we've been able to make some accomplishments. And by the way, just so you know, I do have the Dumbbell Nebula up here. That's what is up here. And you know, it's just like when I first put it up, it always takes my breath away. And when we look at this, you know, really just a beautiful thing. Anyway, I just thought I'd throw that out there. Anyway, you know, when we talk about concepts in the universe that don't make any sense, you know, certainly black holes don't seem to have, you know, an intuitive feel to them. You can't intuitively say, oh yeah, a collapsed star, I get it, singularity, of course. What else would it be? And like, no, that's not how it goes. With singularities, you don't have any logic to fall back on to try and understand them. You know, they're a mathematical construct, and that's about as far as it goes. And you have to believe in the math rather than anything else. And that's just crazy stuff, let me tell you. I tried to understand it at one point, and it's just, it's hard, man. Really, really hard. So, I don't know.
Well, that's why we have you. I can ask these crazy questions, and smart people like you can help try to figure it out. Well, like I said, I mean, it's just gonna be the right perspective of looking at something, or just the right question, just to have that one little trigger to get someone on the right path, right? So
yeah. I totally agree.
We have, okay, Monkey says, now I don't know if this was all like part of one kind of conversation going on, so these might overlap, but Monkey said, I've heard there's a web effect in the universe, something to do with dark matter. Is this true? Like everything's connected like a spider web?
Oh, well, you know what? interesting. When we look at the universe and the way it's laid out, where matter has formed and the voids where the matter does not exist, we see a very interesting pattern. And it does kind of look like, I won't say a web, I'll say it almost looks like a computer network. It looks like a bunch of nodes on a computer network. A very, very extensive, very, very large computer network. And does it mean that that's how the universe is built? No. It means that we see, when we observe the universe, we see these things, and we put them into a context we can understand. To us, it looks like a computer network. Now, that's probably just going to give a whole bunch of armament to the folks that believe in, that nothing is real and that we're all living in a hologram like the Matrix. Because there are people out there that see a movie and then think it's real. And then, like, somehow say, yeah, the Matrix is right. I think they got it right. And it's like, yeah, no, I'm not in a tub of stuff, with a jack in the back of my head living in a, under some alien control. All right? I thought it was a great science fiction movie, but it's not real. I think what we see is what's out there, and I think that the network that is the construct of the universe is fascinating enough without having to add other stuff to it like that, but like I just did. All right, but when we look at the very large scale constructions within the universe, the very large scale formations, the large scale matter distributions, they do have this strange filamentary link between them all, which I can see people likening it to spider webs, but I don't see it as spider webs more so than a computer network. And they're not just like separate little nodes where there's only one thing. No, there's billions of these nodes, so to speak, and they all kind of go together into one and then branch out into millions more. What an amazing image this is of the universe, and you should look it up, actually. I think you want to look up topography of the universe. That might have it in there. Someone in chat will do it. Topography of the universe, and I think it'll have, and just look up in Google, look up in a select image, and you'll probably find this image I'm talking about. And it's not so much spiderweb, but like a network. It looks actually, you know what? I gotta take that back. I don't want to say computer network. It looks like a neural layout of the human brain is actually what it looks like. That means more, I think. It's almost like a neural net, a neurological network. So that's something to check out. Right? Topography of the universe, and I think it's really cool for you to check that out. And yes, my favorite word is cool, and I'll try not to say it too many times. Okay, I'm heading to another object that I want to see, which is really nice, and we've seen it before, well, only once actually. And
this is really weird because I was gonna do this last night, but I didn't realize until halfway through the stream.
Yeah.
So many things that I watch at earlier portions of the day come up later on streams just naturally, and
really,
it's so weird. It was happening all night last night, and I was gonna start making notes.
Wow.
And then I forgot all about it last night after the show. I forgot to tell you all the crazy synchronicities.
Okay.
This one, you saying that the universe kind of looks like a brain.
Yeah.
I was watching, I think it was like top 10 hidden images in famous artwork or some weird little YouTube clip like that.
Okay.
And they were talking about the creation of man by Michelangelo on the Sistine Chapel.
Yeah.
And if you look, and most people will know the picture, it's a man on the left, bottom left, reaching out, and his finger is touching what's supposed to be depicted as God on the upper right, surrounded by angels. But if you look in the background, what God is coming out of looks like a brain, like an anatomically painted brain.
Hmm.
So I mean, and as you were talking about that, chat was kind of going back and forth, like when you're talking about the Matrix and was the creator of the Big Bang God, and just just different fun little theories that people have heard and stuff. And
Cool.
for you to say the universe looks like a brain, and then to think of the creation of man image, it's very, very weird. And it does. So much of human history has been inspired from the universe. That is just, whether you just look up and say, oh, that's cool, or you're a proper astronomer, I don't know how anyone cannot be fascinated by what we're seeing.
Yeah.
Sorry, that was my rant for the night. Okay, I'm
No,
okay.
that's okay. No, and that was a interesting observation, though.
So it's...
Yeah.
I
very
must be
cool.
on the right path, right? It's all coming together. It's little
Yeah.
signs saying...
I think so.
I think so.
I just wanted to show you here, by the way, since I'm doing this. This is low to the horizon, but this is actually M22. It's a globular cluster in Sagittarius, and it's a beautiful globular cluster. And I don't understand why it's. Oh, I do. Duh. I'm looking over and I'm seeing that the moon is almost set, so we shouldn't. The moonlight should be out of the way. But I'm probably going to be out of the way too pretty soon if I'm not. I might have a problem with the telescope. Let me just check. Well, I have it, or I can see it in the light. I'm going to check to see if there's dew. Oh yeah, see, that's explaining it. Okay, I got dew on the telescope right now. The enemy of astronomers all over. We didn't have any dew yesterday because of the fact that it was only 40% humidity. And tonight we do. Oh, is that a joke? No. So let me just do something here. It's amazing how many times you use the word dew when you talk about trying to get rid of dew on your telescope. Yeah. See, it happens every time I point the telescope a certain direction, and I get dew forming on the telescope because the wind is coming through the open shutter, and it carries moisture on it. So right now, what I'm going to do is see the word dew again. What I'm going to do is I'm going to plug in the
astronomer's favorite tool.
Astronomer's favorite tool, which is what?
A hairdryer.
Yes, it is.
Oh, sorry. I hope that wasn't for chat.
No, it wasn't. Was not, because they've heard me do it enough. So I'm going to plug that in, and I need a new one because this one's actually, I plug it in, I go to run it, and it goes, it doesn't seem to start. It started, yay! Hold on. Sorry about the noise. I am sorry about the noise, ladies and gentlemen, boys and girls. We're just going to wait here for the dew to clear on the telescope. And then when we take another picture of M22, it's going to look a little different. Oh, man.
And actually, Steve wanted to know if you would consider tonight's viewing better than last night's.
I do not, but it's still very, very good. We didn't have any dew last night, which meant there was less water vapor in the air. But this is still actually a very, very good night, no doubt. Because I am looking overhead now, and I have beautiful Milky Way, just like last night, just about the same quality. The only difference is that we've got an unfortunate amount of moisture in the air. Okay. There we are. That's good. Okay, I think we're cleared off here. Alright, so now that I'm cleared off, I will leave the hairdryer out, just in case. And I will put down my phone, which I was using for a light. And now, right away, I want to take another image. Let's move the seat out of the way.
And a little side note, last night was probably, I'm sure it was the longest stream you've done. It was almost 5 hours long, and the only reason he had to end was he didn't want to sacrifice his toes for the stream.
Yeah, it was really cold. And it's not winter here, man. It's just summertime. Oh, this is... I did a boo-boo here. I went 12,800 ASA for 13 seconds, so it's going to be fairly bright. We'll have to... Yeah. Well, actually, it's not so bad. But look at the difference. I mean, that's a hugely different image than... Okay, compare... Here's what dew does, okay? This is without dew. I have to take pictures of it at the right... sorry. What's going on here? I want... Oh, did I not... Oh, I took pictures of it. Hold on. There it is. So that's...
Oh, wait, I'm on a delay. That might not be the one you're actually looking at now.
Yeah. This is what it looked like with the dew on the lens, on the thing. And then... This is what it looked like without it. So it's a fairly substantial difference. But unfortunately, what that means is that, you know, I am going to end up running out of time to do anything meaningful tonight with this because of the fact that we have dew considerations. So, that said, I'm going to see if we can check one thing or two out before we have to close up for the evening.
Okay, well, hold on. Let me get some more questions in there.
Okay.
Ben wants to know, well, I think this was probably in reference to Monkey's spiderweb question. Ben says, I've actually heard entanglement and dark matter doesn't actually exist. It's just a misunderstood aspect of higher physics. What do you have to say about that?
I have to say, if you're thinking about quantum entanglement at 12:30 at night, you need to get a life, man. Oh wait, that's me. I apologize. Yeah, well, you know what? And the entanglement concept and what was the other part? What did he say? Entanglement and what?
Entanglement and dark matter don't actually exist. It's just a misunderstood aspect of higher physics.
Well, consider that when we say dark matter, what do we mean? Let's just take that apart. Dark matter isn't dark. I mean, the word dark means only that we don't know what it is. So it would be equally accurate and exactly accurate, in fact, to say matter that we don't understand versus dark matter. The word dark just came into play because dark, it's a black box. We don't know what's in there. Ooh, and that's where that comes from. That's all it means. It's not anything beyond that. So that said, and I'm gonna go to the Trifid Nebula here just for a minute because I want to be able to detect whether we see it the same way we saw it the other night or last night. It's just my way of trying to figure it out, the quality of the night. Okay, here we go. So, as far as entanglement goes, I don't know how to really answer that in a succinct way. So, if we want to talk about this, like the next stream or something, I can start early in the night, and by the end of the night, I could probably have a good answer. Because
okay, well, I'll say that question.
We have to, you have to build into this. You have to build up to being able to discuss this kind of thing, because there's a lot of stuff going on, and to just say it is sort of like a cop out. You have to know what's going on. You have to be able to get a foundational background. You have to understand what's going on in the background before you can actually make heads or tails of it directly. So we can do that. I mean, I have no problem with that.
Okay. He just wanted to clarify. I meant entanglement is the explanation for what people are currently referring to as dark matter. I don't know if that helps or not, but
well,
we can save that for another stream. Yeah, I like the idea of a rainy night talking about dark matter and stuff.
Yeah, no, and what he said actually makes a lot more sense than what I thought he was trying to say. So, you know, now I get it. Okay, what he's trying to suggest is that they're talking about dark matter is really just a version, or we're seeing a version of quantum entanglement, and that could be true, but you know, it's just a theory right now, and we don't even know about entanglement, frankly. You know, we haven't really been able to identify true entanglement. And we haven't been able to identify dark matter. It's just, you know, we just know that there's something out there we don't understand, and we give it names, and that's about it. And this, look at this Trifid Nebula. Holy cow, that's really pretty. That's really, really pretty. I think at this rate is 10 seconds at 6400. Let me see if I can go to 8,000 and not get too much noise at 10 seconds. By the way, on the website, I did upload raw images today. And I did, I say website, a Facebook site, the SkyTour LiveStream. I uploaded some beautiful imagery that we took last night. And I did put up some raw images as well. The raw images are, I say not raw. They're all JPEGs up there right now. But if you want the raw images, and the raw images are a .arw format. Now, what is that? Now, JPEG is a format of a graphic file that really, if there's say a blank part of the sky, then the JPEG algorithm, in order to get a small file, will compress the data and make similar data the same. And that removes data. See, it's called lossy compression. It actually, you lose data with JPEG. I'm taking multiple pictures, yes, that's why I'm doing this blink. I'm doing a bunch of 10-second shots at 8,000, and then I'm going to show you the unprocessed shot and then the stacked processed shot tomorrow. So this is, you know what I should do though? I should probably make sure that I'm fully focused, because if I'm not, I'm going to have to do this all over again. So, oh good, it looks like I am. Looks like I'm as closely focused as I can be for something that this low to the horizon. So anyway, lossy compression is something that we want to avoid, and a TIFF file, T-I-F-F, Tango, Indigo, Foxtrot, TIFF files are good files. They don't have lossy compression, and so when I take images in the telescope, okay, it's taking JPEGs and a RAW right next to each other. So I'm getting two files for the price of one. Okay, and the files I'm getting are a RAW and a JPEG, which is, kind of lossy compression. I use all the RAWs to make everything that I have up on the website, on the Facebook SkyTour LiveStream site. And that said, I uploaded all JPEGs up there so far, and on some of them I wrote unprocessed, try your hand. So you can take them down, and if you don't know the first thing about image processing, then guess what? That's going to be a cloudy night stream night where we're going to actually talk about image processing. So you can actually get a free product that I actually teach all over the country, and I'll be teaching it at Devil's Tower, in fact, in September, at the Devil's Tower UFO Rendezvous. And that product is called IRFAN View, I-R-F-A-N View, V-I-E-W. And that's IRFAN with an F, IRFAN View. And IRFAN View will allow you to do some basic image processing on your images and allow you to do some very cool things. And the other thing that we do you see I'm taking multiple shots of the Trifid Nebula. By taking multiple shots like this, what I'm actually doing is each photo will become a set of data that I can use to create a final photo of the Trifid Nebula. Now, how would I do that? Because I will take each of these images, alright, and I'm done doing that for now. I will take each of these images and I will add them together, stack them on top of each other. And I know some of you in the chat have probably heard of image stacking, and that's what that would be. And to do image stacking, you can download a free product called Deep Sky Stacker, and you can actually get a beautiful stacking process underway. It takes a little learning to get to do it, to know how to do it, but it's something that you would actually be able to do within minutes of the first time you try. So I think that it's cool, and I use that word cool again, and I would like to see you try that. I'd like to see you try your hand at stacking, and I have to give you a bunch of these raw files, which I can do and will do, so that you can try it. All you have to do is let me know. I'm not going to put them up there unless I know that you want to do it. And then I will actually do that with you. I can take you through it. We can actually do it live on the screen. You see, watch it happen. I can just take you through a whole process, and we'll do it. We won't do it in the observatory, but we will do it, on a cloudy night stream night. You see, I'm setting up for doing cloudy night astronomy streams as well. We're going to actually do these whether it's clear to stream or not, because I want to keep streaming. I want to keep bringing stuff to you. And I think it's cool. Yes, we are in the Lagoon Nebula, by the way, and I just want to show you. Look at the lagoon. Isn't this beautiful? And I want to show you one thing, in case you've forgotten. You see the pink part of the nebula there? Right in the center of that, you see that star that's there? Okay? That star is an O-type star. And it's actually sending out such high energy ultraviolet light that it's impacting the hydrogen atoms in this gas cloud, and those hydrogen atoms are absorbing some of the energy, and because they don't like to stay at that high energy level, they spontaneously emit it. And what comes off of them when it does this emission is light. That light is red, and that's what we're seeing here. We're seeing H2 regions, hydrogen doubly ionized. So it's H, Roman numeral 2, H2. And so, these nebulae are the places where stars are born. And this O star was one of the stars born there. They only live a couple 100 million years. And then they are destined to explode in a supernova to return to the interstellar environment those elements forged in its nuclear heart. So I think that the stars are amazing, because how is it that something born of fire and fusion, fire and fusion they call it, born of fire and fusion, that'd be a good name for a book. Born of fire and fusion, somehow ends up with planets and living things and us, and potentially many living civilizations. And this all came from one thing: hydrogen gas. How in the world did that how in the universe did that happen? It's a fascinating mind-bending journey to think about how the universe formed and then life came about. I mean, there's no reason why hydrogen should have made life, but it had to do with forming all the elements in the periodic table from these stars, from the lightest to the heaviest, and then somehow synthesizing creatures. Why would creatures even form? Why not just have stars and planetary things, and why would there be anything resembling life? Why is life? That's the question. Why is life? And that's something we don't really know. You got any clues?
I don't have any clues, but it's a good question.
Yeah. Why is life? You know, and we still don't know what it is. We don't know what makes something alive. We assign qualities to it. We say, oh, it's reasoning. It's self-directed. Um, it makes decisions on its own. Um, and it's not a computer algorithm. It's a decision-making process born of a neural network in a thing called a brain. And this happens with the most complex creature on the planet to the simplest creature on the planet. You know, something as simple as that is, a higher life form, I should say. And so it's an interesting dilemma and an interesting question, something to talk about with people around a fire pit at night, or around a lagoon nebula like this one. So it's sort of an interesting evening, and I'm, as you can guess, oh, that's not a really good picture. Well, the nice thing is I actually have a repair tool that I use. I use some advanced. I have some advanced tools for fixing stars that are a little bit elongated and stuff like that. And it's cool. It'll work fine. Let me just check the telescope. Well, the dew is coming back. What a night. You know, the Milky Way almost looks better than last night. Ay, 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 I tell you, you guys, we're lucking out. We are lucking out. And I want to thank you for coming here. But I am going to
hold some questions over until next time then.
Oh, no, if you got questions, we can do it now.
I do have a few.
As long as you don't mind that there, may not be anything on the screen, because I may be... I could keep taking some pictures until I get a lousy image. So I'll do that. Go ahead.
Well, the last zoom in, that was really, really pretty.
I know, that beautiful H2 region in the Lagoon Nebula, which is Messier 8. Yeah, it's really pretty. You're right. I agree.
Okay, questions.
Sure.
Okay, and again, I'm sorry, guys. These are going back a bit. Ted said, since we only see part of the spectrum, are there things in space that can be seen if we look outside of our visibility spectrum with the equipment of some sort?
Absolutely. Just look at the IRAS, the Infrared Astronomical Satellite. IRAS actually shows us some tremendous details in objects out in space that we never would have guessed, including the data that we got from the Spitzer Space Telescope, which does infrared studies. And the Spitzer Space Telescope, for instance, has found planets around other stars because it's only looked for the heat signatures, the infrared energy given off by these planets that would otherwise escape and elude detection. So that's the infrared spectrum. In the ultraviolet, we've seen many things. We've actually detected stars that shine only in the ultraviolet, and they're very hot, but they're also a lot of their energy is off in the ultraviolet range. A whole new breed of star, and so a star like that, of course, could never host life like us, because we're actually little sensitive little beings. We don't like too much sunburn potential, and that's exactly what we'd get from the UV, and we'd have the different types of UV as well, the UV A and B or whatever. So we have plenty of things that we can't tolerate, and the UV studies showed that there's a lot of those things out there that could kill us, which is really interesting. And then we have, and then with even higher energies, the way we found black holes was by finding these bursts of X-rays coming to the Earth. That's one way, actually, we found black holes. And X-rays are very high energy, which means short wavelength rays coming to us. And when we look for in the UV range, X-ray range, we see things like that. And then at the other end of the spectrum, we go into the longer wavelengths beyond infrared and longer into the radio spectrum. We find that there are what are called radio sources out in the universe. That doesn't mean there's stations out there. Okay, this is just KUNIV. You know, it's not universal radio stations, but they're just radio sources, meaning that some stars and some objects out there give off radio frequencies, and radio waves, radio sources are interesting in that regard. In fact, we can actually, and I built an antenna to even do this. I built a radio telescope, and so in the radio frequency, we do a lot of things to detect stuff from outer space. Arecibo in Puerto Rico is a big, giant, natural dished area, which actually they put a dish in, and it's only able to face up, and it uses Earth's rotation to actually determine where it's pointing. So there are radio telescopes everywhere. George Roll Bank is a big radio telescope. Then
is that what the WOW signal was? Was that a radio?
Yes, it was. In fact, it was a radio wave. See, that's right. The WOW signal was a radio emission that we received. And it's still debated, hotly debated, in fact, whether it was actually just a satellite passing between the antenna and the source. The receiver on the ground and the star. It might have been, but who knows?
Well, that would be easy to duplicate, though. To rule it out anyway, wouldn't it? I would think.
Well, no. And the reason it's not easy is because the satellites all give off different frequencies. And there were no satellites that gave off a known frequency like that, except some of the defense birds, and no one's talking about those. So there was some discussion that maybe the WOW signal was a satellite that nobody wanted to talk about.
Who do we have to find to talk about it?
Well, got to find a president willing to divulge, I guess. That's about it. If we don't have one that wants to divulge, then you ain't gonna get it.
NSA, I love you. You don't know who's listening.
Well, I don't know. Don't forget,
you do. Okay.
I was, I've done classified work for the Navy for over a decade actually, and so I've been living in that world and know some of the things that go on. So I have seen and heard some really strange things. I've even been part of UFO cases that were actually not UFOs but our stuff. And I've lobbied the government to provide explanations to people so that they would know that what they're seeing is actually not a UFO. And I was told, no, you just don't tell them anything. And I said, no, we got to tell them. We can't just not tell them anything, okay? Because I tried to play it this way. I said, if we don't tell them anything, what do you think is going to happen? They're going to think that this is really a UFO. And like me, an investigator of UFOs, what are they going to do? They're going to investigate it. They're going to set up camp. They're going to set up times where they're going to come out with a bunch of people, and they're going to have electronic devices. They're going to look up in the sky. They're going to detect what you're doing, and they will catch you in the act of and probably expose a secret project. So, would you rather have that, or would you rather just give me an explanation that I can give people so they know what's going on is not a UFO? And I got my explanation. I was like, oh, well, since you say it that way, it made more sense for them to provide an explanation than not to provide an explanation.
I'm so glad you said that, because I really wanted to say that, because I have heard you say that in the past a few times but again, I don't want to overstep and say something that might not be appropriate for all streams, but...
What's that? What do you mean?
I saw something, and the government's like, oh, don't tell them anything. I mean, Not that it's anything major, but even if it is, and it's none of our business, well, no matter what you say, we have to tell them something, you know?
Yeah,
Like,
yeah, exactly.
without divulging secrets that are going to hurt you, obviously. Don't lie to the public because they're not going to buy it. So what's the point, you know?
That's right.
And
Yeah. I agree with
which
that.
is another reason that I like this channel so much, because you do tell it how it is and you are upfront and honest with people. Because people don't know you. Yeah, you're showing cool stars and giving us cool information, but who are you? Why should I believe anything you have to say? You know? Because this is your background, this is your life, this is what you've dedicated yourself to, and you know, so.
Yep.
Anyway, Dave wants to know, what do you think of the M drive?
The M drive is
Dave Shock. That was from Dave Shock, by the way.
Dave Shock, how you doing, Dave? So good to have you in the stream tonight. Is he still there?
He was doing dishes. It's
doing dishes.
About 11 o'clock there, maybe. He should be around, Dave.
Yeah, maybe he is. Well,
he should.
I think the M drive is fun because it can't work, yet it does. And numerous people have confirmed the results. Now, what does it mean? What's the M drive do? The M drive is actually basically think of it as a rocket nozzle with no propellant, and you have to have a little magnetron inside an M drive motor, so to speak. And what's a magnetron? Well, a magnetron is what drives your microwave, and it generates these microwaves. And when you have this magnetron in there that's very passively generating microwaves, the microwaves are bounced around in this cavity. This is called a cavity thruster too, and there's a little more to it than that. But the microwaves are bounced around in this cavity, and then they are, in a sense, you think of it this way, they actually get directed out the back of this nozzle. And when they do, they generate thrust. Absolutely amazing. And so the M drive, and it's spelled EM, by the way, the M drive was a really fascinating device. I thought that was really cool to see. Oh, there's that word again, cool. I thought it was really interesting that it even worked at all. And I looked up the physics of it not a week ago, just to get a feel for, whether this was a real or potentially artificial construct of people thinking they're seeing something when it's not. But too many people have reproduced it. So I do believe the M drive is interesting, but I have to say, the M drive is not capable of taking us interstellar. No, not in any reasonable amount of time. See, the M drive is actually very slow. I mean, when we talk about force and thrust, we measure this, the thrust of a rocket in millions of pounds of thrust, or tens of thousands of pounds of thrust coming out of the back of the rocket, and that's many tens of thousands or hundreds of thousands of newtons. A newton is a unit of thrust, a unit of force, and the M drive only generates a few micronewtons. So, yes, you get a positive thrust, but it's nothing that can propel a ship off the planet into space. In fact, it's nothing that can take a ship out of orbit, even. Now, if you have a ship in, say, a low Earth orbit, well, one thing that can happen is that the ship can just, maybe accelerate to higher and higher orbits, using the M thruster, the M drive. But because the thrust is so small, it's possible that the atmospheric drag, that is the stray molecules here and there that strike any ship that uses this, might actually cause the thing to might actually cause the M drive to never really be able to accelerate. It might be just enough resistance, but we don't know. It's all to be tried, all something to be tried. One of the controversies was that the M drive was said. It was said that the M drive could only work in a vacuum, like in space. Yet they got mixed results on that too. So the M drive is a great possibility. I look at it as a stride forward in science, as opposed to a unique answer to all things interstellar, because it really isn't. We don't know. We don't know where M drive will lead, but I can say this: I think that it's going to get people thinking. It gets us going. I just think that the drive from Miguel Alcubierre, that he developed in 1994, that's the warp drive, by the way. I think that is the most fascinating potential tool that could take us interstellar, and that would put us within reach of stars like Alpha Centauri in just, realistic trip travel time of 2 weeks, and that's something that is fantastic when you consider that a trip to Alpha Centauri would otherwise take, at the fastest speed that we know how to travel, 19,000 years. So 2 weeks is quite a bit less. I mean, we could even do that.
It's stopping is the hard part.
What's that?
Stopping is the hard part.
Yeah, well, technically you have to turn around and start thrusting in the opposite direction at the halfway point in your trip, right?
But didn't you say maybe it was something else? Didn't you say that there was something that could get to us to Alpha Centauri, but by the time we stopped, just us stopping would cause such an explosion in front of us that it could destroy, like...
Yeah, think about it. Think about it this way: as we are traveling through space using our wonderful warp drive, what we find and what could happen is that we would, just like we see as we drive down the highway, we collect bugs on the windshield. We would collect energetic particles on the front of our warp bubble as we're speeding the universe past us. And I say it that way for the reason I'll tell you actually shortly. So when we got to Alpha Centauri, what would end up happening is that we would stop suddenly, the warp bubble would dissipate, and all those highly energetic particles would go in the direction that they think they're supposed to go, and that's toward our destination. And if that happens, literally, we might as well have sent a killer solar system bomb to another solar system, because it would actually destroy the whole solar system, star and all. That's how much energy would be released if we did the trip in, say, 5 days, because it can do that in 5 days. That's the theoretical possibility. So to make it more realistic, we have to do it in, say, 2 weeks, so that this extra energy can be bled off little by little, and we could slow down in a more leisurely pace. But 2 weeks to Alpha Centauri sounds like it's great, over 19,000 years. But that's for a star that's 4.3 light years away.
Is that 2 weeks of Earth time or time on the spacecraft?
That's well, actually, here's the funny thing. It'll be both, because we wouldn't be subject to relativistic time dilation. If you're familiar with science fiction, you know that in science fiction they sometimes will use this as a tenet of their shows, and that is that if you travel near the speed of light, time slows down for the occupants of the spaceship, and meanwhile time passes on Earth. So in other words, there's a famous paradox called the twin paradox, and some of you in chat know that. The twin paradox is a paradox where a 30-year-old man leaves the Earth, goes to, say, Alpha Centauri at the speed of light. It takes him 4 years to get there, okay, at the speed of light. And he turns right around and he comes home, and the total trip time for him was 10 years, okay? Now, he didn't go at the speed of light, because nothing can go the speed of light and survive as a corporeal thing, like a human being or a body or whatever. So he had to go near the speed of light, and if it took him, say, 4.4 years, 4.5 or 4.6 years even, to get to Alpha Centauri, and he turned around and came home, then he would find that everyone he knew and everyone he ever loved had long since died centuries ago. Or at least, tens of years ago. And that's because, and his brother, his twin, would, of course, no longer be alive. This is, potentially. So this is part and parcel with what happens when you start to play with relativity. Now, the Alcubierre drive is different, because if Miguel Alcubierre if his drive really works, then we don't use Einstein postulates to travel through space. We don't use light speed. We defy it. We go around it. In fact, we travel many times the speed of light. Because if you think about it, 2 weeks to Alpha Centauri means we got to go 4.3 light years. That is, light takes 4.3 years to travel that distance. We would go 4.3 light years in far less time. So how would that be? How could that possibly be? Well, it could be if we're actually traveling in a way that defeats light speed. And what is it? That way is actually if we were to imagine this. Put a warp bubble around our ship. So we have a ball around our ship. And that ball is a special type of space. But from within that ball, the rest of the universe can't touch us, see us, or act on us in a way that could cause us to be constrained by its laws. So, whereas the universal speed limit is light speed, we can violate it using the Alcubierre drive. And the way it works is, we would actually, from our ship with a warp bubble around it, we would actually compress the distance, shrink the distance between us and our destination, but then lengthen the distance between us and our origin. And that process, which of course is just a theoretical thought process for now, is actually under investigation by NASA. And there's one particular scientist leading that charge down at NASA, and it was because they figured out that the Alcubierre drive could be accomplished and the warp bubble could be created using far less energy than they thought it needed. In the original design by Miguel, he actually came up with a warp bubble requirement that the energy to make the warp bubble, warp bubbles don't exist, by the way, they would have to be constructed, and to make the warp bubble would require the energy equivalent of converting the whole planet Jupiter to energy. That is really way beyond anything that any civilization, probably even an advanced one, is capable of in this universe. So it became a thought problem. Haha, that was really cool, Miguel. Neat tensor you came up with. But then some years ago, another group decided to redesign Miguel Alcubierre's ship, and they designed a warp ring that was a little bit different in geometry. And changing the geometry, because it was done as a let's see what happens kind of a thing. And changing the geometry made the Alcubierre energy requirement to build the warp bubble and construct the warp bubble out of energy 10 to the 26th times smaller than required before. What that means is, in practical terms, never mind the exponents, is instead of a mass equivalent of the planet Jupiter converted to energy, it was the mass equivalent of a Voyager spacecraft converted to energy. And now it became practical. Now it became a possibility, even a dim, distant one. And that's why NASA's been funding research on this, because It's a real possibility now. Is that not the coolest thing? We might actually have developed an idea for interstellar travel, and we basically still don't know how to get along together. Um, we still do weird things in this world and torture each other and hurt each other. Yeah, interstellar travel? Oh yeah, we're on our way. But who wants us out there? Who really wants us out there? We have to do a huge amount of development, personal development, before we become an interstellar species. That's my opinion. Anyway, long drawn out answer. I apologize.
Well, I was loving it until the kind of downer at the end of humanity, but
Well, it's true.
that
Though, isn't it?
it's so crazy. I had to mute because I started laughing. That paradox is so crazy. My brain started tingling.
Well, I'm sorry about your brain, but you can actually look it up to get the numbers.
I know, I love it. I love it.
Because the numbers I gave are not exactly correct. You'd have to look up to get the right numbers. So I apologize.
Yeah, well, I love paradoxes and because that's the thing.
You
That's
and
what I
Martin
do.
Gardner.
Ask why, right?
Right.
And
Martin
if there's
Gardner
no
loves
answer, it just drives me crazy. So I love them.
Mhm.
I absolutely love them. That's very cool. And our good friend Jude is in the audience. I don't know why she hasn't been made a mod yet. Probably because you're too far away from chat all the time. So
I am, but are you able to
hopefully we can.
are you
See, I don't know if I don't think I can mod people.
Can you make her a
No.
mod? If you can, that'd be great.
I can't. I didn't think I would be able to. Or I
Jude-
would have. But
Jude is actually Jude is wonderful. She's actually she's the person who runs the FX Models Planetary Replica Division out in Arvada, Colorado, where they're based, and it's another group for FX Models that we started out there because they were the appropriate talent and to do the job in creating these giant planets. And the folks that paint them are the most talented people on Earth. And I, not just saying that because they work for me. I'm saying that because I wouldn't have them working for me if they weren't. This job is critical. We've done jobs for NASA. We've got a large-scale solar system model in Istanbul, Turkey, at a science museum where they're very, very keen on making sure that everything is right. So they had us do it. We've had inquiries from all over the world for making these planets. I guess people like planets, you know? I mean, that's a good thing. So I'm glad she's here. I'm glad she's out there listening. You know, she's obviously very important to me because she's basically shouldering this entire group out there on her own and on her own shoulders. And you know, she runs into issues from time to time, but she handles them very well, and I'm very, very happy with what she's done. And she's also a Cherokee Indian, which kind of falls in line with my Native American mother. So I'm very happy about that, you know, because I understand Native American people are a different breed, no pun intended, than other people, and they tend to embrace the earth, and they tend to embrace the things they learn in a different way. And it doesn't say that the way some of you that aren't Native Americans are wrong. It's certainly not what that means, because I certainly get along with everybody this way. But I just really, I just have been able to relate very well, especially in business, with someone who has the same type of mentality as I do. And I attribute it to being Native American, part Native American, but you know, that's just me. It may not even be that. It might be something totally different, and I'm just an idiot and don't know what I'm talking about for sure, possibly. But I don't know. But anyway, I just wanted to do that shout out too, to let her know that you know, and say publicly that they're doing a great job out there.
Yeah, and you can also check them out on Facebook, FX Models Planetary Replica Division, through the link in chat. They are a proud sponsor of SkyTour LiveStream with Mark Antonio. And she's also going to be down at Devil's Tower with you in September. That's
she's
very, very exciting.
Yeah, and she's bringing a bunch of well, I don't know if I should say it out loud. Well, okay. They're planetary models that I'm going to use in my lectures. I'm doing lectures on Thursday, I'm sorry, the Friday, the Saturday, and the Sunday. I'm doing lectures all 3 days at Devil's Tower UFO Rendezvous. Um, and we're going to be uh, using the models with a little bit of electronics and some special effects to kind of showcase my lecture. I don't want to give it away because it's going to be on video. I'm sure they're going to videotape it. And if they don't, I will. And if they're not going to videotape it, then here's what I'm going to do. I'm going to SkyTour LiveStream it. I will. I promise.
I think you should anyway, or get the video of whoever tapes it and get a copy up here anyway.
I'm thinking about that. You know, I definitely want to, because I'm going to bring my high-end camera. So there's no reason that I can't live stream this. As long
It'll
as
be promotion for them too.
Well, as long as I have Wi-Fi, you know, I'd have to, you know, be able to connect it. I think my laptop actually has an HDMI input, and I do need an HDMI input to do this. So I might be golden already. I don't know. I'll have to check. Anyway, I did wanna say that if we have any questions left, can we move them to next time? And could you remember to tell me next time?
Yes, I will save them. Yeah, we do actually have a few questions left. So
okay. Well, give me one more. Give me one more.
Well, okay. Well, this actually, I think this will be an appropriate one for the ending. Ted wants to know, what would you suggest for proper use and/or maintenance of a scope? General things one should keep on hand.
Okay, that's a very good point, and I have one right here in front of me, which you can't see because it's dark and it's down below, but this jumbled mass that I'm sort of passing in front of you here, and I can, let me put the light on here. This jumbled mass, oh, there we go. See, now you can see it's green. Okay, this is a cover for that, okay? You need to have a cover for your scope, and even if you store it indoors. I'll tell you why, because if you don't, what will happen is you will end up getting, potentially getting, rust showing up in places on your scope you didn't want, or you know, would hope would never happen, but you'd get it. And so you need a cover for the scope. You also need to make sure that the clamps on the different axes for the scope are not too tight, because if they're too tight, then it can deform that little area on the shaft, and then when you go to tighten it someday, you might be just to the side of that area, and it could end up causing you problems. It could end up not engaging right. The other thing you want to consider is that your telescope you want to get has to be portable enough so you can take it where you want to take it. This beast behind me is not portable. This thing here was meant to be in an observatory. We only got it because we were going to put it in an observatory in a building. And it belongs in a building. It doesn't belong out on the lawn on a big tripod. Okay, it belongs on a steel pier. Okay, so you have to buy the telescope that is appropriate for you know, what you're planning on doing, and that's where I'm going with that. And I think my microphone is actually dying now. Can you hear it?
Just as you said it, I noticed it distorting a little.
Right, folks, right. I'm going to say goodnight now.
Good night, chat. Thank you all for joining us again.
Yeah. People leaving. Oh no, I'm ripping out of here. I'm sorry, folks. Good night.